It was a great event, but after that,
Accelerated the pandemic.
It's really bad decision for regulation.
When is the next one? So it'll be like
In 24. Yeah, next year. Out of nowhere. Chair, I have 5 sessions.
whoa,
Shape them.
Yeah.
You know, define the topic. We really do it.
because ESA really does.
Yeah,
it.
they really do it.
Okay.
It's really cool. I think
Sure. With the okay. Good morning, everyone. It looks like, as Elias said, a lot of people had too much wine last night, so it's a little bit empty this morning. But you who are here are the hardcore remote sensing hydrologists. So we have an interesting session this morning. The title is Novel Technologies and Future Missions, the Future of Water Cycle Research. And we have a diversity of talks from ESA and the Italian centers. And we're starting this morning with Elias Daras, and he's going to be speaking about mass change and geosciences international constellation magic.
Good morning from my side. Thank you, JD. So I would like to give you some prospects of the ESA-NASA Mass Change in Geoscience International Constellation. And I start by giving you this figure that shows you the fleet of satellites already in place and planned by ESA. And in this circled item, you see MAGIC, where it is actually the plant. We're in the phase B1 now of the development of NGGM, where MAGIC is considered to be the next mission of opportunity in the frame of the future RIO programs at ESA. So some words on MAGIC. What is MAGIC? It's the ESA-NASA collaboration because we had signed an MOU in June 2022 with NASA, where gravity mass change was listed as a priority for cooperation. We have a long time history of discussing cooperation in satellite gravimetric topics with NASA, and we ended up with the concept of the MAGIC, which is the concept for collaborating on future satellite gravity constellation, addressing the needs of the international user community. The aim of MAGIC is to extend and improve the time series of gravity missions, providing the time-varying gravity field measurements at enhanced spatial and temporal resolutions, with reduced uncertainty and latency in order to address international user needs expressed by bodies like IUGG, GIGOS, and so on, and also, very importantly, demonstrate operational capabilities of the mission. What does MAGIC consist? It's a Bender-type double-pair constellation, which is going to be realized in a staggered approach. The first pair is the Gray Sea pair. It's a NASA DLR program. Actually, it's almost the same concept and design as Gray's follow-on. It's going to be launched at the same altitude with the same more or less instrumentation. And the second pair is the next generation gravity mission, is the ESA pair, to fly at around 70 degrees inclined orbit at around 400 kilometer controlled altitude. And the goal is to have minimum 4 years of combined operations for MAGIC, with a goal to start at 2032, where the mission is going to be launched. We want to have higher resolutions, shorter latencies, and higher accuracies in order to enable new science applications and demonstrate the operational services that can potentially be useful for the Copernicus services. Few words on NGGM and its baseline concept. The NGGM, the next generation gravity mission from ESA, will be in an inclined orbit, as I mentioned. The spacecraft will be identical, embarking a laser tracking instrument, 3 accelerometers, and GNSS receivers, among others. It's going to be a European laser tracking instrument as a baseline, and we're discussing optional contributions from NASA with units suited for NGGM. 3 accelerometers are planned. The performance is consistent with the main instrument on board, which is the laser tracking instrument performance, and they're going to be provided by Onera from France. We plan to have hybrid propulsion using xenon as singular propellant with the heritage of Gotze, electric propulsion with Minirid thrusters. for orbit maintenance, drag compensation, and the system of linear cold gas thrusting for fine altitude control and drag compensation. Vega-C is baseline launcher, and the date of launch is no later than 2032, with a minimum lifetime of 5.5 years and targeted lifetime of 7.5 years. Just this is a busy slide. What are the priorities? We'd like to have long-term monitoring because this is a prerequisite for delivering reliable trend estimates. The longer time series, the better we are positioned to provide answers to questions of ice mass loss, sea level rise, and so on. Climatology is important for climate applications, and satellite gravity data, derived indices like floods or drought monitoring are important. But at the same time, we need to increase the spatial resolution to properly monitor catchment basins, small than what we have been doing so far with the GRACE. And of course, this will allow for a better closure of the water budget. And it's also important for ice, ocean, and solid earth applications. Increased temporal resolution in combination with shorter latencies, providing data not every 3-4 months, but 2-4 days, and depending on the offline products, every month. This will facilitate fast-tracked application services with direct applicability in water management and evaluation of flood risks, for example, issues of cost of vulnerability, etc. This, at the same time, will enable improvements at longer periods because we're going to be, with the constellation, able to capture and estimate short-period solutions, reducing aliasing effects. Uncertainty is also very important. We need to reduce the uncertainty of the products, of the level 2 and level 3 products, in order to go closer to the requirements that are defined by communities of IGG, GIGOS, and also the ECV requirements that are the essential climate variables defined by GIGOS. And these are reflected in the official documents from ESA and NASA, the emission requirement documents for MAGIC, and also the ESA's NGGM emission requirement document. At the same time, important is to have consistent homogeneous quality products at a given period, and this is important for enabling services and as well as for science purposes, because we know that GRACE flies in a free drifting orbit, resulting in alternate ground track partners and variable quality products. We want to have, with the MAGIC, operational services that require consistent quality products. In that case, it's important that we can achieve this by controlling the satellite orbits, at least of NGGM. We have seen that this is one of the very important aspects. Some words on the performance before I dig into some science topics. I don't want you to understand these curves here, just need to make a point here of the differences we are looking at on the mission performance at different resolutions. So we look at the level 2 monthly products. These are unfiltered products, and the performance for MAGIC is supposed to look 10 times better at degree 40. This is around 400 kilometers, and 80, which is, I don't remember exactly, 250. So we're looking at improvements that stem from actually the choice of the inclination of NGGM altitude choice, flying lower, and also improve instrumentation. So the level 2 products of MAGIC will lead NES post-processing, and ideally not at all, because they're going to be their certainty levels are going to be meeting the requirements for the mission, and that is very good because then you avoid all effects you can have in terms of smoothing of signal and spectral leakage. NGGM will provide consistent quality products, as I mentioned before. So just to go to the thematic fields of the mission, here you see in the what is defined that the mission is going to contribute to. We have hydrology, and you see subtopics there. I'm not going to read them all, but I leave it there: hydrology, cryosphere, oceanography, and we continue with solid Earth, climate change, neutral atmosphere, and geodesy. So a big gamma of science topics and applications for the mission. You see that satellite gravity is at the heart of observation science applications. Now, I selected some of the objectives of NGGM and MAGIC for different time scales. Of course, we're going to look at sub-weekly time scales, monthly, seasonal, and long-term time scales. One of the objectives is to measure and monitor the mass change and improve current estimations of groundwater storage, soil moisture, water balance closure, and assess the global change impacts on water cycle. And of course, provide the capability to raise extreme events warning. Another objective, as you see, I've skipped some because they're not related to this conference, is to provide mass and sea level change and heat estimates for oceanography, improve tidal and ocean circulation models, and this information is crucial for operational oceanography and marine forecasting services. One of the other objectives is to measure and monitor the mass change and its trends for climate change applications. And last is to provide measurements of the ocean mass change and trends for estimation of global ocean heat uptake, ocean heat content changes, and earth energy imbalance. This is an example of expert from the mission requirements document. This is an ESA official document. You can see the citation there. You can also download it. It's a public document and see exactly what we aim to do with the mission. Give an example for hydrology. We have the timescales here, and you have some examples of what is the resolution accuracy at the moment of unfiltered GRACE follow-on data. And this is what we expect to have with the threshold uncertainties of NGGM and MAGIC, where you see we have novel products at 3-5 days. That is not possible to have with GRACE without being post-processed. Monthly cases, we go to higher resolutions and specific uncertainties that are more stringent to GRACE. And then long term, we need to go to much higher resolutions and reduced uncertainties. Now here I give an example of the 5-day products and its importance on hydrology. We look here at simulated results, synthetic experiments. So on the left, we see the grounded distribution of a GRACE-type polar pair solution. And here we have the MAGIC one, which is a constellation, as you see here, and the ground track pattern sampling the Earth. And there we have taken, this is part of the ESA studies of the phase A. The results shows the temporal root mean square deviations of basin average water storage variations. For 5-day solutions, we have actually taken the uncertainties of the fields and then projected them at the basin scale and compared it to a truth reference signal, which is taken from the ESA Earth system model, hydrology and ice component. And we have truncated this at the degree 50, which amounts to a resolution of 400 kilometers. And we did it for the largest basins worldwide from the GRDC database, 405 basins. And you see here that the uncertainties are much larger in case of a polar pair, where this is drastically reduced with the constellation. Again, these are synthetic experiments, but shows you what is expected at level 2 unfiltered products, so not post-processed, not smooth. The same representation in terms of histogram here shows you that for the required accuracy set by the international user communities and groups, we have a very good compliance to this requirement for all the basins here, or most of them, at percentage of 93 for NGGM and MAGIC, whereas with a polar pair you have you cannot reach that at all for the 5-day solution. That means MAGIC brings strong improvements over the polar pair for continental hydrology, enabling the terrestrial water storage monitoring of small river basins at the required accuracy. The accuracy, as again I have to mention, has been set not by ESA but by international groups and experts that have been helping on shaping the mission requirement document. These are user needs. So as you saw, I said again that we will enable the 93% of the recovery of these basins at the required accuracy at 5 days timescales. Moving forward, hydrology and extreme events. So this is an exercise, a synthetic experiment again. The same again. This time is on the left. We have the constellation, and on the right you have a polar pair type synthetic experiment where we try to assess the wet extreme scoring of detecting the terrestrial water extremes. These extremes were actually defined of the 95th percentile of the variability of the ESA-ESRIN model, which actually uses the LSTM, terrestrial water storage variations. LSTM is a model from GEFSET. So this is the background information, and then the 95th percentile was set as to be to find the extremes, and we see how well we can capture these extremes in a synthetic in the closed loop environment. As you saw here, as you can see here with the polar pair only, the gray areas represent regions where you have only false positives in simulations. So the error and the uncertainty is so big that you get a detection of an extreme event only by chance, and because it's due to the error and not due to the real signal. This can happen in a real-time application if you don't know exactly how to validate the information from the satellite missions. So in this case, you have a confidence for MAGIC that you will have much less or gray areas, only for very small scale features here. And you will have blue, which is optimum score, much more than red, and which is not so good. And all the white areas is nothing else but there was no extreme detected from the model. So it's really worth to look at the colored areas and also the gray ones here. So important that MAGIC 5-day product will be a novel contribution to monitoring of extreme, including droughts and floods. And this is very important for introduced to be in the operational services as part of the data simulation techniques, because this is, of course, a very important topic. Now, some words about another water application for oceanography. What we see here are, again, synthetic experiments for determining the ocean bottom pressure variability, where we see that MAGIC brings dramatic improvements in the explaining the variability at 80 to 90%. First of all, for small basins like the Caribbean Sea, so smaller enclosed seas, we can see that the requested 1 centimeter RMS variability is explained by 80 to 90% of the variance if you look at the plot of the curves here, whereas with the grace kind of simulations, it is hardly explained also at very low resolution. But here we can go up to 120 spherical harmonic degrees and orders, what actually is the gravity field representation. And very importantly, another topic is the monitoring of meridional overturning circulation, which is actually this feature here that goes a stripe along the coastline of Northern America from the North Pole down. This is a very important signal for oceanographers and for ocean modelers that will be monitored and will be sensitive by MAGIC. And this is also something that is it's a novelty of the constellation. An application now for the climate will be that MAGIC will be able to observe and quantify climate changes that lead to intensification of the global water cycle. What you see here is 30-year projection of the CMIP 6 ensemble global model, and how the simulation can capture changes due to that. So in terms of amplitude or change at this case, and you see that the MAGIC compared to a graceful on type scenario can detect changes at a much larger percentage. 36 will go up to 64 for the amplitude, and for the phases up to 56. That means it is important to validate also climate models, and in the future, even though think about trying to integrate these observations there. This is a very complex graph, but I want to make a point here that MAGIC will produce novel products that will have an additional content that is currently part of the gray solutions, and that is the atmosphere and ocean averaged content, which is currently being removed during the production of level 2 products due to remove the aliasing effects. So these are models, the aliasing models removed by the observations to arrive to the hydrological, let's say, signal. This contribution can be added again to the GRACE observations to arrive to the full AOHIS signal, so they are including atmosphere, ocean, non-tidal atmosphere and ocean, but then it comes to the expense of having the contribution of the uncertainties of this model, which is actually one of the biggest error contributors to the error budget. Importantly, the constellation will give you the ability, due to the increased spatial temporal sampling, to actually monitor directly the full column of the signal, including the AO. And this has some important applications in terms of, for example, storm surge prediction for flooding at the places of the ocean where at 5-day modes there is a basin scale mass change exchange between Pacific and Atlantic. And we have seen that this has been not well monitored, and models are poor to this, and definitely MAGIC full AOHIS product would be very valuable for testing and developing models for these processes that will be useful for storm surge predictions for flooding effects. Very fast, because I'm running out of time, I want to show here that satellite gravimetry is very important for, can be also potentially used for Copernicus services. For example, we do have some experiments also including the early warning system for drought and floods at the GLOFAS, for example. This is not integrated yet, so they were in the prototype case. But we do have these essential climate variables of terrestrial water storage and groundwater that are provided merely by use of satellite gravimetry, and can be prototyped and implemented into the Copernicus services, so that we have terrestrial water storage provided as a service in the future. And for this, I give you an example of this project from the European Commission, where they worked really on extracting from satellite gravity the groundwater storage product, using, of course, information from other services for snow water, for lake water and river discharge, subtracting all these effects from the gravity and arriving to the groundwater product. And this is in a prototype phase, which can be really used as an operational application in the future and feed many important services. So the conclusions here is that we have MAGIC, which is the ESA-NASA two-pair constellation concept based on the GRACE and ESA as NGGM missions. MAGIC is expected to extend and improve the time series of gravity missions, satisfy user needs of the international community expressed by this by different bodies like IGG and GIGOS, and demonstrate operational capabilities in anticipation of adoption into operational services. There is a big benefit for water science. Exemplarily, I give here the better closure of the water budget, quantification of water cycle change. We aim to quantify better the anthropogenic changes in climate and land use, and water storage interact, and also monitor this Atlantic meridional overturning circulation for oceanography in timescales of years and decades. But importantly, we have, this is my almost my last slide, water-related operational application and services. For example, by enhancing the temporal resolution at 3 to 5 days and reducing the latency of the products, we will contribute to monitoring of the weather extremes, using and assimilating them in early warning services for drought and floods, improving the ocean bottom pressure estimates that is useful for ocean circulation models and operational oceanography and marine forecasting. The enhanced spatial resolution and reduced uncertainty will contribute to operational groundwater and river runoff discharge monitoring that is very important for water management and freshwater availability. So, and also it's important to use the MAGIC products to validate and potentially to integrate into the climate models. And also the last point is that the constellation will provide novel signal content, including this non-tidal atmosphere and ocean that can improve storm surge models used for coastal flood warning. I leave you with this slide. We had a very successful workshop 1 month ago at Assisi in Italy, together with NASA on the constellation, where you can go and visit the website. We have all the presentations uploaded with very rich material about the constellation, and also GRACE, because we need to see where we stand and where we want to go. Of course, you are free to go and check the presentations there and the conclusions of the workshop. So thank you very much for your attention.
Thanks, Elias, for the talk. Are there any questions? Audience? Yeah, Jerome?
Elias, you're not being a good boy. We asked for a recommendation slide. What do you recommend to a space agency involved in
As a space agency, I recommend to myself we implement this mission. This is why I didn't put the slide. Yeah.
Is there anything unfinished that needs to be supported by like something we can write in the report of this workshop that would?
Yeah, it's very important by the hydrological community to define the priorities, thinking about satellite gravimetry in mind. So what satellite gravimetry can contribute to hydrology, especially for operational services, thinking about bringing this thing into at the next level is useful for operations.
Okay, you signed a few lines that we copy paste into the report.
Of course, of course.
Thank you. One quick question about the 5-day operational early warning. 5 days is what you integrate on, and then what is the latency? When can we get this 5-day?
Every, I think, 2 to 4 days.
So 7 days between the beginning?
This is a more, this is not defined yet, but every 2 days you can get a 5-day update. And there are ways that you get even a daily update of these 5 days if you use some moving window Kalman filter approach, but this is still investigated.
So if we want to predict flood, we have to think of being capable of predicting like 10 days in the future with a 5-day project.
The important is that the information there is going to be much more related to real signal compared to like the so-called daily daily fields of grace for the moment, which are very smooth. So you will have real information there in these fields.
Okay, thank you. Any recommendation from the scientists? Because 2 people from ESA are talking to each other, and we'd like the feedback from the scientists, and there's time at the discussion to enhance this discussion.
Yeah.
Thank you.
Okay.
Yeah, very brief question. Do you expect an improvement in the geoid, or gauss-derived geoid will still be the gold standard for space geodesy?
Well, the static geoid is very well measured by gauss, so no improvements there. But in terms of temporal variations of it, yes, and this is important for the geodesy applications then. Also, when you think about perhaps precise orbit determination of every observation satellite, you need to have this information better retrieved.
Elias, can I ask a quick question? Yeah, the operational objective goal target, which requires a better constrained orbit. You kind of mentioned this. Does that imply an architectural change, something propulsion or something?
Of course, but this is the baseline of NGGM. So it's considered to have a drag compensated system that not only maintains the orbit but keeps it in a position where it's important for all the applications, and you have also the propulsion system contributing to the fine attitude control and provide you a very good measurement system.
Great.
So, yeah.
Okay. Yeah. Thank you. Thank you. Okay. Let's go to our next talk. We have Daniel Casella from CNR ISAC. Welcome. Great job, great job, great job.
Good morning. I will talk you about the HSAF program from EUMETSAT for the development of the EPS second generation algorithm for MWI and MWS for snowfall and rainfall precipitation rate retrievals. Well, the HSAF is the satellite application facility for operational hydrology. We have 3 clusters, so-called clusters, for developing new products. One is about precipitation, liquid, solid, instantaneous rates, and accumulated rates. soil moisture cluster and the snow cover characterization cluster. More than that, we do an independent validation of all the products and evaluate their contribution for operational hydrology. Within the precipitation products, we have two main classes of products, one based on microwave observation, especially passive microwave observations from a large number of different instruments from the GPM constellation, essentially. And these are the level 2 instantaneous precipitation products. These are orbital products of instantaneous precipitation. And these products are then regridded and resampled in time in order to have a more usable product based on microwave only retrievals with a 30 minutes time step. There's also a product based on the inversion of the soil moisture content. It's called SM2-RAIN. It's another level 3 products that contributes also to the level 3 products. Then all these products together, these microwave-based products, are combined with the geostationary infrared information in order to have a near real-time precipitation monitoring tool using MSG, Meteosat second generation, and in the near future also the Meteosat third generation. These are microwave and infrared combined products. So about the level 2 products, we in the last years have developed a number of different algorithms based on different approaches, and there was an evolution of these approaches. We started almost 10 years ago with a retrieval technique based on Bayesian theory and a training data set based on cloud resolving model and radiative transfer simulations. And we evolved into a neural network-based approach. We kept the simulation-based data set, while at a certain point we moved to an observational-based data set based on spaceborne radars, essentially the GPM dual frequency radar, the DPR. In the last generation of products that we have developed, we used both a machine learning approach and an observational data set, this time based on two different radars. The DPR for liquid and mixed precipitation and CPR for snowfall precipitation. In this way, we can use the retrievals from a large number of different satellites. And this is the temporal coverage over the day in mid-latitude north, let's say, in Europe. And we can almost have a 3-hourly coverage. So we get at least one observation from one passive microwave instrument every 3 hours. But in some times of the day, in the early morning and in the early afternoon, we get an hourly coverage. So these two new products for the two radiometers that are MWS and MWI, they will provide instantaneous precipitation rates on a global scale from the EPSSG, MWS, and MWI. These products are designed to start producing operational products since the first day of measurements being available for users, and they will estimate both rainfall and snowfall rates, instantaneous snowfall rates at the surface. For the development of these products, we used the two existing radiometers ATMS, that is a cross-track radiometer, quite similar to the future MWS, and GMI, which is more similar to MWI. All algorithms are based on machine learning approaches, and they have been developed up to the end of this year. We expect. Oh, there's an error here. The launch of the first EPSSG mission is due in the fourth quarter of 2024. And then when the dissemination of the data will start, the operations also for these products in the distribution near real time will start. At a certain point, after at least 1 year of observation, we want to produce a new algorithm based on actual observations from MWS. A similar approach is followed for the second satellite, the EPSSG-B, at the end of 2025. We choose this instrument as a proxy for the future radiometers because the central frequency observed by these instruments are very similar to the future MWS and NWI. We selected a number of frequency, and of course there are some channels that we have not used and we will not use until the development of the day 2 products. For the MWS, these very high frequency channels, the 2029 gigahertz, and for MWI, the 118 gigahertz band. These are a complete novelty in the passive microwave radiometry. For the MWI radiometer, we needed to average also the brightness temperatures in order to meet the lower resolution of the future MWI. For the building of the dataset, we used CPR, that is a 94 gigahertz frequency cloud profiling radar, very accurate also for measurement of instantaneous snowfall, and the DPR, especially the KU band measurements for rainfall ground truth, let's say, or reference. So we built 4 datasets, one with CPR and GMI, another with DPR and GMI, and then CPR and ATMS, DPR and ATMS. This dataset has a quite different population. The DPR GMI is a huge dataset. The 2 instruments are on the same platform called GPM Core Observatory, while the smallest one is the CPR GMI for snowfall. We collected all coincident observation within 15 minutes of the 2 instruments, and we divided the dataset into training and tests. The scheme of the algorithm is this one. We have a collection of input data, essentially the brightest temperature that are regridded in order to overlap every center of every channel. There is a radiometric calibration that will be developed after the launch of the missions, and some ancillary dynamical parameter coming from ECMWF forecast are added to this set of inputs. The first step of estimate is a phase classification into, let's say, ice or snowing and mixed or rainfall producing clouds, and then a series of modules for the detection of snowfall, supercooled droplets, and the estimate of snowfall and rainfall follows. In the meanwhile, we produce also a series of intermediate products that can be quite useful also for many different goals other than just the snowfall rate estimate, also for modeling, checking, and validation. We produce a snow water path product, a detection of the supercooled droplets in snowfall clouds, and ice clouds detection based on CPR. And we also produce the rainfall rate estimate, of course, an ice water path estimate, and liquid water path estimate in the mixed phase clouds. The results of this algorithm are quite satisfying. These are the main comparison between our algorithm and the DPR in an independent set of data. We have a small root mean square error, quite a good accuracy, quite an high correlation, and limited bias for the rainfall or mixed phase rainfall rate, instantaneous rainfall rate estimates, but also for the snowfall rate products. In terms of detection, these results for detection of rainfall rate and snowfall are also quite satisfying. The same happens for MWS, which is a cross-track scanning radiometer, quite a little more complex in terms of measurement, because this time we have a field of view that an instantaneous field of view size that changes with the scanning angle. But again, we get satisfying results in terms of root mean square error and accuracy for both snowfall and rainfall, and also quite good detection statistics. For these last products, ATMS or MWS and CPR for snowfall estimate and detection, we tested also various different machine learning architectures in order to make a model selection. So we tested both pixel-based shallow neural networks that are, after all, the one that we chosen, or both for the high accuracy that we have got, but also for the simplicity and the operational needs of these products. And we also tested some deep learning convolutional neural network algorithms. One more simple is called VGG, and the other is a quite deep architecture called ResNet. We also tested more simple schemes based on the decision trees, random forest, and gradient boosting algorithm. And what we found is that, after all these modules have, all these approaches has quite good results, both in terms of detection and estimate. I'm sorry. But at the very end, the best performances came from shallow neural network or VGG, especially for the detection problem. A comparison with the NASA GPROF for ATMS of this algorithm. GPROF is the state-of-the-art algorithm for passive microwave retrievals. What we found in terms of relative accuracy is that this algorithm, in both estimating snowfall and rainfall, has better results, a little better results than GPROF in all rates of precipitation. Precipitation for both rainfall and snowfall rate retrievals. This is a similar comparison against GPROF divided by the surface of observation, over snow, over ocean surfaces, and over land. Well, the results are quite good in comparison with GPROF. one thing that appears is how difficult it is to estimate and detect precipitation rates, snowfall or mixed phase precipitation over snow cover surfaces. GPROF has very poor results in this task, while our algorithm is quite satisfying. Also for ocean and land, we get better results, but less impressive. So in order to conclude, we could say that in our study, machine learning and satellite radar data are essential to build new accurate and fast algorithm for the precipitation estimate using passive microwave radiometers. In particular, the snowfall detection and estimate from the future MWS and MWI will be achieved with good accuracy using these machine learning techniques. In perspective, deep learning techniques have a great potential, but they are related to the observation geometry of the instrument, particularly tied to observation geometry of the instrument. Our plan is to implement these techniques in the day 2 algorithm using real data. We are waiting for the Erker mission. It will be essential for the future snowfall algorithm development. It would be possible to exploit other missions from using passive microwave radiometers, such as the ESA-ESRIN constellation, the SIMR mission, or the Feng-Yung passive microwave instruments. After GPM, we used the DPR radar a lot to develop our algorithms. What will follow? We wait for the NASA guided AOS mission, but it's quite far. And we are also waiting for the Feng-Yung 3G radar that should be decommissioned soon, and for the data from the Tomorrow.io, a private company that has launched a number of KA radar, and we are waiting for this data to be released. Recommendations. Again, satellite precipitation cloud radars are very important for this work. They are essential for the passive microwave algorithm development. Very important will be the missions at high frequency, 94 and higher, such as Erker and also Wyvern. About the rainfall radar missions after GPM, well, we will rely on non-ESA missions, but for some of these missions, we are wondering what will be the accuracy of these products and what access will be provided to European researchers. About machine learning, these techniques, especially the deep learning, require a very large data set, and the access to data can speed up the training process. We have seen that the European Weather Cloud could be a way to do that. The problem is that every user has its own need, and the access to the specific data that we need may not interest a large number of users. About the radiometers, we think that the strategy that the agencies seems to follow is quite good, very encouraging. The approach to have the two most advanced instruments from the passive microwave radiometric point of view, that are MWI, MWS, and ICI, that we are not using in this work right now, but it's a very innovative instrument that are a long-term perspective mission. And together with that, a constellation of small medium satellites such as AWS or more constellation of small satellites can be a very good approach for improving the time sampling of the observations and have also reference standard measurements and satellite radiometry. Thank you. Thank you very much.
Thank you, Daniele, for the talk. Very nice. Are there any questions from the audience? Yes?
No, not much really. There are two LEO mission with KA radars from the Chinese agency. One of that has been already launched and they are in the commissioning phase. So we are waiting for the data to see the first data, make some comparison. The good thing is that we have right now the NASA radar, the DPR, so we can compare with what we know in order to see the accuracy of these instruments. But no, I don't know much.
Please.
Thank you very much. Looking forward to it. Just to know if you think that later you will be able also to compare with, for instance, radar from the surface. So surface radars, not the ones on board. And what do you think about this in the future? How to compare it and use it also, of course, surface observations?
What I haven't said is that we, for the satellite products that we provide in the HSAF program, we do operational comparison against carrying gauges, against radars, and also hydrological based validation for some basins in Europe, a number of basins in Europe. Of course, comparing the satellite radars with the ground-based radar is a very, very good point. Thank you for the suggestion. Of course, it is something to do. What we do is to develop the algorithm using satellite radar as ground truth, as reference truth, because it is the same instruments. It guarantees at least the coherence of all the measurements. So it is almost a global observation for these two main reasons.
Thank you for the questions and thank you for the answers. We'll have to move on now for our next talk. Thank you very much. And our next speaker is Andrea Camplani from CNR ESAC also. Welcome, Andrea.
No. So good morning all. I am Andrea Camplani. I am a postdoc researcher at the Institute of Atmospheric Sciences and Climate in Rome, offering to the National Research Council of Italy. Today, I will show you some results of a research activity carried out by me and by my colleagues Paolo Sanò, Daniele Casella, Leo Daddario, Giulia Panegrossi, in collaboration with Professor Alessandro Battaglia from Politecnico di Torino, about the evaluation of snowfall retrieval capabilities of the new ESA mission Arctic Weather Satellite. So, snowfall retrieval is a quite challenging question in the field of atmospheric sciences. Regions where snowfall is predominant, such as polar areas, are poor in ground-based instruments, so it is necessary to exploit satellite observation. The best estimation from satellite of snowfall are obtained by using meteorological radars, which, however, are characterized by a very limited spatial coverage. And so it is necessary to develop a retrieval method based on passive microwave observation, which are less correlated to snowfall parameters, but ensure an higher temporal resolution and an higher spatial coverage. In the last years, several machine learning-based algorithms for snowfall retrievals based on passive microwave observation have been developed. So, the passive microwave retrieval, snowfall retrieval, is based on the fact that the upwelling radiation is scattered by the presence of snowflakes in the atmosphere. And as a consequence, the brightness, we can observe a cooling in the brightness temperature observed at high frequencies, as you can see in this plot. However, we have to also to consider the fact that the presence of supercooled droplets generates an emission effect which causes brightness temperature warming, which can partially or totally mask the typical scattering effect. And this can be a problem because a large percentage of the snowing clouds are characterized by the presence of supercooled liquid water layers. Currently, these layers are detected by using combined radar lidar observations. However, these products manage to detect these layers on the top of the clouds, as you can see in these plots. The supercooled droplets are represented by the purple points. But these products sometimes fail in detecting these layers if they are embedded in the cloud. In this context, the new AWS ESA mission could be represent a very interesting tool for snowfall retrieval. In fact, this mission consists in a polar orbiting satellite which ensures a high temporal resolution over high latitude areas where snowfall is predominant. Moreover, the satellite carries the microwave radiometer, which is a cross-track scanning radiometer characterized by 19 channels, which cover a frequency range from 50 GHz to 325 GHz, which is a frequency range higher than the frequency range of the previous cross-track scanner, such as NOAA Advanced Technology Microwave Sounder and the EUMETSAT Microwave Sounder. And it's a good innovation for snowfall retrieval. So the main purposes of our activities that was founded by ESA-ESRIN project has been the analysis of the detection capabilities of supercooled liquid water layers of the new radiometer, and the analysis of the added value of the 325 GHz channels, which represent the new tool with respect to the previous radiometers for snowfall retrieval. We based our activity on the analysis of a simulated brightness temperature dataset. The simulation have been based on 7 days of clouds and Calypso full orbit observation. In particular, we use the ice water content, liquid water content retrievals from Captivate product, that is the official EarthCAR product, now based on CloudSat cloud profiling radar and Calypso lidar. We apply a radiative transfer model based on an Eddington approximation and on a gas absorption Rosenkranz model, and we use the scattering tables derived from the Rayleigh-Gans theorem. The supercooled liquid water layer detection, we have analyzed the detection capabilities of the supercooled liquid water layers by focusing on a case study, which consists in a cyclonic event near the Canadian coast that has been observed by the cloud profiling radar and by several radiometers. I will show you the coincidence observation with micro humidity sounder. And if we observe, in the plot, you can observe the CPR reflectivity profiles and the captivate ice water content, liquid water content retrievals. So we observed that in the northern part of the event, we have a shallow cloud system, and in the southern part, we have a deeper cloud, which corresponds to a quite intense snowfall events. We also can observe that in the northern part, captivate product managed to detect the presence of supercooled liquid water layer, while in correspondence with the deeper part of the cloud, this type of layers are not detected. So in the plot, you can observe, in the top plots, you can observe the comparison between the MHS observation along the CloudSat track and the simulated signals obtained by applying several Rayleigh-Gans models. In the fourth plot, there is the CPR reflectivity, and in the bottom plot, the ice water path and liquid water path retrieval from captivate are reported. So we can observe that at 89 gigahertz, in correspondence with the cloud anvil, MHS observation shows a TB increase that is not present in the simulated signals. On the contrary, in correspondence with the deeper part of the cloud, the simulated signals show a TB decrease that is not observed by MHS. A similar behavior is observed also for the 157 gigahertz channel, while for the at 190 gigahertz, there is a good agreement between the simulated signals and the observed one. So we hypothesize that this difference are due to the fact that there is a supercooled liquid water layer that has not been detected by captivate product. And so we decided to create a new scene by adding this type of layer. In particular, we did two experiments, one by fixing the elevation and by varying the liquid water path, and the second by fixing the liquid water path and by varying the elevation. We can observe that by adding this layer, at 89 gigahertz, we have a good agreement in correspondence with the cloud anvil between the observed and the simulated signal. Moreover, the TB decrease in correspondence with the deeper part of the cloud is less important or almost null. Moreover, we also can observe that the liquid water path variation has an influence at 89 gigahertz, while the elevation variation has an influence at a higher frequency channel. So we decided also to simulate the AWS MWR signal. Here you can see the signal for two channels of the oxygen absorption band, in particular one external channel, one internal channel. So we can observe that the supercooled liquid water layer has an influence on the external channel and has no influence on the internal channel. And as for the 89 gigahertz channel, the liquid water path variation influences the TB increase, while the elevation variation shows no influence. On the contrary, at higher frequency channel, we observe an influence of the elevation of the layer. and the influence of the presence of the new layer become less important at higher frequency, while the sensitivity to the presence of ice in the atmosphere, also with low ice water content values, become more and more important. To analyze the added value of the 325 GHz channels, we have to consider the fact that these channels have been designed to be coupled with the 183 GHz channel present in the instruments. In fact, you can see by the plot on the right that these channels show a very similar weighting function in clear sky condition, while their sensitivity to ice in the atmosphere is different. So we try to simulate the differences between two external and two internal channels of the two water vapor absorption band, and we can observe that this difference are very sensitive to the presence of ice water content, while in clear sky condition the difference is almost zero. The external channel shows higher sensitivity to ice in the atmosphere, and the presence of a supercooled liquid water layer has an influence on the difference between the external channel, but is a slight influence, and has no influence on the internal channel. We also did a study over the entire data set. In this plot, you can see the scatter plot between the two external channels of the two bands. And so we can observe that in clear sky condition, the differences between the two channels are almost zero, while in presence of ice in the atmosphere, the difference become larger. Moreover, we trained two neural networks, one for ice water path retrieval and the second for the surface snowfall rate retrievals, with and without the 325 GHz channels. And you can see by the table that the statistical score become better by adding the 325 GHz channels. In conclusion, we can say that AWS can represent a very interesting tool to improve snowfall retrieval capabilities. In particular, we can exploit the differences between the channels in the two water vapor absorption band. Moreover, it is very interesting the fact that we can exploit this radiometer to detect and to characterize the supercooled liquid water layers. In particular, we can exploit 50 GHz channel and 89 GHz channel to retrieve the liquid water content, and the higher frequency channel to retrieve the elevation of this layer. And so in a future perspective, the synergy with also active sensor observation will be very interesting. For the future, we think that in AWS satellite constellation will be very interesting to improve the global snowfall quantification. And to do that, it will be very important to develop snowfall retrieval algorithm based on the observation derived from the AWS prototype. And it will be interesting also to exploit the synergy with the archive radar, and to also to exploit the synergy with the new radar mission for snowfall retrieval. Thank you for your attention.
Thank you, Andrea, for the talk. Very interesting. Good work. Are there any questions? Can I ask something? Maybe what was the most interesting thing you found, or the thing that surprised you the most in doing this research?
I think that the capability of the radiometer to detect the supercooled liquid water layer is a quite interesting task, and I think that we are now working to focus on this argument to deepen. And so.
Yeah, I really appreciate your analysis of the individual value of the different approaches to measuring these things. I thought that was really thorough, really interesting work. Thanks.
Thank you.
Okay, let's move on to our next speaker. Thank you. Next speaker is Alessandro Battaglia.
Hi.
Welcome, Alessandro.
Thank you. So I will try to discuss a little bit about spaceborne G-band radar. So G-band is an additional nomenclature from radar meteorologists, another letter, but it simply means frequency between 110 gigahertz and 300 gigahertz. So we're talking about wavelengths between, let's say, 3 millimeters and 1 millimeters. This is work that have been done together with Pavlos Kollias at Stony Brook. And yes, the topic here, water cycle, of course, but we are talking, as the previous two speakers, about cloud and precipitation. And specifically, what we are looking at is cloud and precipitation in the atmosphere. Before understanding how much precipitation is falling down, you have to understand what's in the atmosphere. And of course, we know that in general, even from the climate perspective, clouds are very important and actually are not yet very well understood. The climate sensitivity changes drastically depending on the feedbacks that clouds and precipitation have. And to understand these feedbacks, you have to understand, there is no way, you have to understand the vertical structure of cloud and precipitating system and their microphysical structure. So you need to understand where the clouds are, where the precipitation is, but also you need to understand how much precipitation there is, how much content there is, and what kind of size the particle have. So as you have seen, of course, because precipitation and clouds, they have a lot of temporal variability. There is no way with a single radar you can do the job. Of course, you would like to have constellation of radars, but the main job is done by the radiometer. But the radiometer you have seen, of course, they have passive, so they have a signal that needs interpretation. And you have seen most of the algorithms nowadays, they rely on a calibrator, which is a radar calibrator, can be GPM, can be at the moment, the previous colleagues, they discussed about GPM, the NASA GPM, or the CloudSat, that will be healthcare. The problem of this mission, most of them, GPM was the first attempt to do a dual frequency radar, but most of them, healthcare, CloudSat, they are single frequency. The problem with single frequency is that you will get where the clouds are, but when you go to, so the detection will be good. So the detection will be good, but the quantification, how much is raining, how much cloud water you have, and so on and so forth, will be a little bit more challenging. So now what we advocated, and we wrote a couple of white paper on that, is that you need to use multi-frequency. Now the multi-frequency, of course, the multi-frequency radars. Why you are using multi-frequency radars? Well, of course, you know remote sensing, how it works. If you want to look at a particle, which is a centimeter particle, you will tend to use a centimeter wavelength. If you want to look at smaller particles, we will use a millimeter radar, for instance, right? So that's why we are going towards the millimeter range. You have seen that the same transition is happening in the microwave spectrum, in the passive microwave spectrum. You have seen how we are moving up in frequencies. So this means that we are becoming more sensitive to smaller particles. But if you want really to understand the passive microwave signal, you need to have a radar out there. So the point is, and in particular, if you want to be more quantitative, you need to have multiple eyes, multiple wavelengths, and a radar system with multiple wavelengths. So now in this picture, you see, in our planet, we have different kind of structure. We have, of course, a shallow system in the poles. So we have a higher system in the higher convective system in the tropics with larger particles. So of course, the combination, the right combination to use will be fine-tuned to the region where we are looking at. If you are looking at the polar region, smaller stuff, drier environment, you will use higher frequency and combination of higher frequency. So there particularly we'll see that the G band will be particularly effective, but also for ice clouds and also for light rain, the G band will be particularly effective. So what has changed in the past years? Well, these cloud radars, actually, the first cloud radars in this G band were built actually back in the 80s, but they were not seeing much. Why? Because they didn't have enough power. They didn't have enough sensitivity. Now there was a game changer in the past years, millimeters and millimeter solid state power devices and low noise amplifier, which made basically this radar now capable of having the right sensitivity to see things. Of course, the big problem of G band, so you see here the G band, you see of course, that is the transmission of the atmosphere, the attenuation of the atmosphere. Of course, the problem that we go higher up, of course, the atmosphere, even in the window regions, and specifically there is a channel which is the 238, which is 238 gigahertz is an ITU allocated for active sensor. That one, you see clearly that you have quite some attenuation from the atmosphere, from the gases themselves, water vapor essentially. So of course, this means that as you go higher in frequency, and if you're looking from down, from the space downwards, of course you will be attenuated by gases, but this will happen only when you hit, let's say, well, below the freezing level, let's say, when you start having really humid stuff. So now, as I said, there was this game changer, and after this game changer, actually, we built G-band radars. So there are now G-band radars operated. Actually, I was part of this UK COI GRACE, well, GRACE, the same name as the Adam Bishop, but means G-band radar for cloud experiment. In this case, was built by RAL and is now deployed at Chilbolton Observatory. Similarly, there is another effort from NASA, JPL, where they're actually building a triple frequency, KEA 3594 and G-band 238 gigahertz radar. And they have actually operated in March, April this year off the coast of California. And there is a paper coming out soon on that. So what means that we have now these tools available with radars operated on the ground and taking measurements. Now, actually, by the way, these are the kind of specs that they achieve with this G-band radar from JPL. Actually, quite nice sensitivity, minus 50 dB. That means that we will be able to see really, really tiny stuff. Now, just to tell you about the Chilbolton experience where I was involved, these were the first light. Actually, we were delighted to see that. I mean, you see on the right-hand side, this is a 94 gigahertz, so CloudSat healthcare kind of eye. And inside you have the G-band. What you see clearly is difference between the two, and it's actually in the difference between these two signals where we try to extract actual information. We look at them, in this case, from the ground. You have the advantage that you can collect spectra as well, Doppler spectra, and you can use this Doppler spectra to much better understand the microphysics of what's going on. The key message that I want to deliver today is that because you are using different frequencies, for instance, in this case, you have seen an image at W band and an image at 200 gigahertz. You're using different wavelengths. So this means that you will have, the return will be different because of the scattering. The scattering will be different. So we call about this, I mean, especially if you have targets in what we call the Rayleigh scattering. So if they become comparable with the wavelengths, they will scatter in a different way. So this means that the cross-section will be different. So indeed, what we see when we look at different radar return, in this case, these are two different spectra, you see that they see, I mean, in this case, actually, we see the different spectra. So this means we are looking at the backscattering return of each single particle, if you want, of each single dimension. We see clearly that they are very, very different. The red is the W band, and the blue is the G band. So the backscattering cross-section are very different. In particular, they are less, I mean, they are smaller at the larger frequency. And basically, we use this differential signal to do what? To do sizing, for instance. Okay. So you look at that difference, and you use that difference in the return to infer the size. And actually, you see here, I have a plot where I have this DFR. What is this DFR? This is exactly the difference in the reflective power, if you wanted. In radar terms, we talk about reflectivity. And you see that difference. You can measure that difference. Let's say you get 10 dB difference, which means a factor of 10 less, like you see, well, in this case, 14 dB. And you see, you can, of course, retrieve the characteristic size of the particle size distribution that you are observing. So very useful because you really get the dimension of the raindrops in this case that you are observing. Now, if you compare on the right-hand side, there is the same thing, which is the basic plot of GPM. GPM is a KU-KA radar. And for the same raindrops, you see the signal is going up to 2 dB, right, for a diameter up to 1.5 millimeter, which is, so now in raindrops, typically raindrops, the typical diameter that we are dealing with is of the order of few millimeters, 1 millimeter, 1.5 millimeter, maximum 2, exceptionally 2.5 millimeter. So you see that the dynamic range of the signal that we have when we use, for instance, a Ka-G band is extremely much higher than the dynamic range that, for instance, you have for KU-Ka, that is the GPM concept. So what does this mean? This means that the sensitivity is much better. Not only the sensitivity is much better, but also you can go and size particles which are much smaller. So essentially for GPM, it's impossible to size anything that is lower than 1.5 millimeter, right? And in our case, we will be able to size, for instance, raindrops down to 0.4 millimeter. So, okay, I think I can skip this because it's very technical. Now, another example, just another nice picture, again from Chilbolton, looking, this is a precipitation system. You see very light rain. Of course, here we are very interested in light rain. Actually, you have seen from the plot before that the algorithm, they do very well, the precipitation microwave, they do very well up to 0.5 millimeters per hour. And then basically, they completely go ballistic somehow with lowers. Why? Because GPM practically has a sensitivity limit in terms at around 1.2, 0.5 millimeters per hour. So light rainfall is practically impossible to have a proper calibration. Now, G-band will be effective in that. You see here, we are talking about, you see the rain rate at the very top, rainfall rate of the order of 1 to maximum 2 millimeters there, I see. And you see, this is an observation from the ground simultaneously with 2 different eyes, Ka, 35 gigas, and 200 gigas. Now, what you see here is clearly, first of all, the colors are completely different, which means it's good because you have a completely different signal that you can try to use. But what you see practically, you see that in this region here, can I use this? Yes, in this region here, you see that there is quite some attenuation, quite some, you know, the reflectivity is decreasing very, very quickly. Now, what is this? Well, if you look at the same image, now I computed the DFR, so the difference between the two frequencies here, and this is an image from the LiDAR. So what you see is boom. You see the LiDAR is seeing here, what is this? This is a cloud layer. So all of a sudden, in a cloud layer, you see that you have a very strong difference, a very strong gradient in the differential reflectivity. Oh, this is the holy grail of radar meteorology. If we are able to see clouds, liquid clouds, then, I mean, we are done. Why is that? Because, of course, liquid clouds, and in fact, there was discussing about the supercool layers inside snowfall. This is critical to understand the passive microwave signal, but it's very difficult to detect by a radar because a radar, the very tiny cloud droplets will not produce any reflectivity. But in this case, we will see the cloud droplets as differential attenuation if we have 2 eyes, one at 35 and one at, let's say, G-band. Same thing for ice. This is, again, another campaign that we did actually back in 2020 using, this was not, well, again, is a G-band, but was another JPL radar at 166 gigahertz. But you see, again, this is a nice cloud as seen by 3 different eyes. 167, 94, and Ka. The point is, you see, there is not much difference between the Ka and the W, but all of a sudden you see a lot of difference here. Now, this difference, again, has to be related to what are the size of the ice crystals that are in these ice clouds. And again, you see that the dynamic range of the signal is much, much bigger if you take, for instance, a Ka-G difference, more than if you take a W-Ka difference. So this, again, is signal that then can be interpreted in terms of size of the particles, okay? And remember that having the size of the particle also will improve how much amount you have, because of the radar signal. We know that the radar signal is very much dependent on which kind of size you have. So if you improve the retrieval of the size, you will also improve the retrieval of the quantity. And again, for ice, of course, it's very difficult. But remember, scattering by ice becomes very complicated because, of course, ice has a variety of shapes, a variety of densities. So you need to, again, to understand the passive microwave, you need to understand in first place with an active tensor how the scattering mechanism works. Now, in terms of what we are doing with ESA, we are doing this Renka study, which is more oriented in looking at the potential of the G-band on top of the AWS study that was discussed before. We are trying to understand the importance of the G-band in terms of producing these kind of things. Plus, we have another study, which is more technology-driven, where we are looking at two options, a Scout class and an Earth Explorer class kind of option involving a G-band. And these are some of the technology that will enable that. I can tell you, of course, very important, having large size antennas will be good because remember, the key thing is to achieve enough sensitivity. So you need to have enough power. So this will be essentially solid state amplifiers. This will be having large antennas or deployable antennas. In this case, for the Scout, this will be a deployable antenna. So we are studying how to deploy this antenna at 238 gigahertz. Of course, we are studying, Thomas Keating is studying actually the quasi-optics related to the antenna, and RAL is more into the receiver, the transmitter and the receiver hardware. This is for the Scout, so critical will be to have a deployable antenna. For the Earth Explorer kind of things, we can think big. In this case, we are thinking about a Ka-G combination because dual frequency is key to get enhancement. In this case, again, very important will be the antenna. In this case, the antenna will be a deployable antenna, Ka similar to the SIMA technology. And of course, very important will be the EIK, so the extended interaction klystron, to produce enough power, again, to get enough sensitivity. And this, of course, is already developed by CPI in Canada, but they can improve on how much power they can transmit there to improve the sensitivity. Okay, so now maybe I want to I can skip on that. We are doing spaceborne simulations. Again, we are using scenes that we derive from the A-train. We are deriving, you see, we are simulating essentially all this frequency, Ka, W, and G for different scenes. In this case, this is a snowstorm at latitudes around 50 degrees north. And we are basically simulating, for instance, as a function of the sensitivity of the radar, how many clouds, for instance, a G-band radar will be able to detect if the radar has a sensitivity of minus 30 dBz as a function of latitude. Of course, we see the typical pattern, but we see a lot of clouds. And again, the key thing is that over the tropics, we will not be able to sense the clouds, let's say, below the freezing level. But over the high latitudes, we will have a wonderful instrument to detect essentially almost all the clouds, except, of course, heavy precipitating mid-latitude system. So conclusions, I hope I convince you that G-band is now a reality. Okay, so these radars up to 300 gigahertz, up to 1 millimeter wavelengths, they are now operating. We have essentially two systems operating, one in Europe and one in the United States. Soon, actually, there will be the University of Cologne is developing an airborne demonstrator. So it will be very important to continue, to continue these field campaigns, because we need to really understand how different wavelengths can work in synergy, both from the ground and from an airborne perspective, which of course is different. But remember, the airborne perspective for a G-band is advantageous. Why is that? Because the water vapor is in the boundary layer. So if you look from upward, you will not be attenuated by the water vapor in the boundary layer. You will be able to see all the ice clouds and start penetrating the precipitation. And actually, if it is light precipitation, you will go down to the ground. So more field campaigns, technology development. Of course, we are developing this technology. Keep developing. We want deployable antennas because, of course, this will give us gain, will give us sensitivity. Development of the transmitters, both in solid state and EIK. and of course all the antenna field network also that goes with that. SRL, of course, we need to advance the SRL. I mean, we have in mind that we want to apply either to the Earth Explorer or to the Scouts Call, ESA Scouts Call. This means we have to, refine the science requirements. We have to improve the end-to-end simulators. We have to improve the level 2 retrievers, so we have to work a lot on these retrievers and the synergy with the high-frequency radiometers. Now, something out of the box, but somehow we have also to start thinking about to develop stuff above 300 gigas. We have seen that the radiometers, they are all going with ICI and AWS above 300 gigas. So why not going also radar-wise higher than 300? Actually, there are two bands that are interesting for water vapor absorption. And finally, remember ITU allocation. So it would be very important that we keep an allocation to this radar system. And I finish just saying that, I forgot about this, but somehow in terms of recommendation, I think because there is an interest between what we are doing here in Europe and we are collaborating with our partners, the JPL in particular, I think it would be good if somehow the agencies, they find a way to merge the efforts and try to go for such a multi-frequency mission. So I conclude here. Thank you.
Thank you, Alessandro. Very interesting. Are there any questions? Please.
Very interesting indeed. Just maybe I missed the field campaigns that you are doing when in Europe and the United States. Where are they doing? What's the latitude range you are covering?
Yes, very good question. Because in fact, the one in Europe is in Chilbolton, so it's close to London latitude, let's say. The other one was in California. So these are very low latitudes. Specifically, the one in California was looking at these low-level clouds, this stuff that is, very low. I mean, clouds that are very important from the climate point of view. That's the point. We should go in the Arctic. We should go high altitude, high latitude, because it's where the G-band will give the maximum, will be at its best. Because you don't want to avoid the attenuation of the humid environment. Okay. But that's one thing. Yes, we have to go and make field campaigns in high latitudes. That's a key. Time to deploy in Canada, in northern Canada, or at the arm facility in Alaska, an arm facility in Alaska.
Another question? Anyone? I think as a remote sensing hydrologist, I love hearing the phrase that if we achieve this technology, we're done. This is what you said, right? We complete the task. So
Say that we are done. Did I say that?
I think you meant like we are
Holy grail.
we are wholly capable.
We have to push, but at least I mean we are able to build a ground-based instrument that gives some sensible result.
Yeah, of course. Yeah, something that can really help and fill a gap that's really missing. Then it makes sense. Yeah, absolutely. Thank you. Okay. Thank you, Alessandro. Great talk. Next up is Ricardo De Collet from CNR ISAC. Welcome, Ricardo.
All right, so good morning, everybody. So yet another presentation from CNR ISAC. So today I'm gonna discuss with you this application of like trying to predict droughts at a short-term scale. So you might be, I guess, used to predicting droughts. Or I mean, trying to assess that, like doing some drought analysis at like seasonal scales. But what we're trying to do here is trying to exploit like data at higher frequency, higher temporal frequency and like the advantages that are coming from deep learning models to do this kind of analysis. And so this is actually part of my PhD program. So this is my PhD research also. So in collaboration, I mean, also sponsored by the University of Naples, Federico II. Right, so I'm sure I don't need to convince you that droughts are, particularly worrying phenomena, and especially droughts are projected to become more frequent and intense in the coming years as a result of climate change. And particularly the Horn of Africa is an area of the world which is particularly affected by those phenomena, and that's why we chose this area as a case study for our application. There's some literature out there that points out that it's actually, it is required to use like some other remote sensing instruments to assess that, like to analyze this kind of phenomena, especially using instruments that have better spatial, temporal, and also spectral resolution to understand all the different characteristics of this phenomena. And especially what we have found that geostationary products are not really well used in this kind of applications. Yes, like some researchers before point out that if you use like traditional polar orbiting satellites, clouds are gonna affect a lot your instruments, like your NDVI or vegetation composites that you're gonna derive. So that's why we choose actually to construct vegetation series with the MSG-CVD, which basically has a temporal resolution of 15 minutes. So you have images every 15 minutes. And also, like some researchers before showed that, especially in the presence of droughts where, which can happen during, for example, during the rainy season, you might have even more clouds, right? So it's like particularly difficult to measure this phenomena during these seasons. And of course, well, yeah, like with new, when new radiometer will come out, like we will be able to extend the temporal resolution of our study even more. So this is the area of the study, and you can see, well, the mean of the daily NDVI derived from our sample. The area has a bimodal pattern of rainfall, so you have a long and short rainy season. And there are some specificities depending on if you're more in the Ethiopian area or Somalia, which is more desertic, or if you go like Kenya, there's some highlands in Kenya and especially in Ethiopia. So this is the data I'm gonna show you for this demonstration. We have used both ERA5 hourly retrieval aggregated into daily precipitation. And also, as I said before, we have used data from CVD at daily. So basically, we took like one image per day from CVD. And this is actually also how we have divided our, our data set for the analysis. So, splitting as usual for training set, validation, and, having an independent test set. So due to the fact that, like the NDVI series had some, well, they were requiring some pre-processing steps. So yeah, after collecting the images from the EUMETSAT data tailor, then, like, as I said before, following this assumption that the maximum daily reflectance is achieved at around noon, we collected images for this period of the day. And then we applied some BDRF method for atmospheric correction. And also we used some white tail filter, which is basically also to reconstruct the vegetation phenology and also to, account for the problem of clouds. Yeah, so here what I'm gonna show you is like the median over the whole sample of our dataset. So as I said before, it's ERA5 precipitation. Here we have actually used a standard precipitation index at 90 days, because as I said before, we wanted to focus more on the short-term aggregations. And so compared with our NDVI, and what you can see here immediately is the fact that, you know, the two series are, you know, follow quite similar pattern. So actually, when we talk about agricultural drought and meteorological drought, we see like quite a good correlation between the two. What we have seen here is that at the end of 2010, during actually the harvest season of 2010, there was like the biggest agricultural drought of our sample. However, using standard hydrological index, like using just the standard precipitation index was not enough to understand, you know, like to see this drought, this agricultural drought coming. And actually what I've, so I don't know if, so this one actually is just a box plot of the raw precipitation, and you can see that here this gap is basically pointing out that with respect to the climatology, there was like a rain event, like there was like a meteorological drought of about 20 days. And also here you can see what's happening in 2009 and 2010 according to the standard precipitation index. So here basically we were coming from a year where there was a meteorological drought, then there was this precipitation event, like precipitation drought, and the SPI index actually recovers and goes over the median. So it seems like that from hydrological perspective, everything is fine, you know. But actually, as I was saying before, the picture was quite different, because at the end here we turned out to have like a quite intense agricultural drought. So the point I'm trying to make here is that using just this index is very hard to see those changes in vegetation coming. Which of course, you know, we all know that, you know, vegetation is not only influenced by precipitation, but of course it's like one of the most important phenomenon to take in account. So this basically motivated us to, you know, do some research in this daily, especially given the fact that we saw that drought of 20 days, you know, that was very hard to see at monthly scales. We tried to research if like the daily temporal resolution helps in obtaining more skillful prediction of vegetation in the future. If, you know, like how sophisticated, how good is our model to do prediction in the future, if we are able to do prediction at 10 days, 15 days, or even, you know, 1 month ahead. And then, you know, we tried different deep learning architecture and try to see what are the benefits of using one rather than another. And this is our, like our approach. So we are trying to forecast vegetation in the future just by combining maps of vegetation and precipitation in the past. We also aim to, you know, extend our analysis with other ancillary variables in the future, you know, like including other, like for example, soil moisture, and so on. And so the first model that we used was actually coming from the spatiotemporal deep learning literature, which is a convolutional LSTM. And basically this model is like using a series of convolutional LSTM layers, and basically this combines the benefits of using recurrent neural network structure, which is able to see, you know, model relationship over time, and also like the convolutional abilities of a model. So like basically to be able to model spatial relationships. However, in order to apply these models, you need to sometimes, you know, like include some artifacts in your data set, which is like I'm showing here. For example, when you have missing values, like some missing pixels, you need to impute. Or for example, in what was particularly struggling in our case was the fact that like the Horn of Africa has a lot of, like you have the sea, of course. So basically, especially for those pixels that are near the coastal areas, like in the convolutional operation, like those pixels are gonna be, you know, entering your convolutional filters. So basically, this is going to skew a bit the results of the analysis. And this is why actually we are thinking about, as a next step, well, we actually started doing some applying this kind of model. It's also possible to use some graph convolutional neural network approach. So basically, if you think of, as a pixel as being, you know, a node, and edges being the relationship between one node and the other, or one pixel and the other. So basically, modeling the spatial relationship, you can also apply this kind of deep learning architecture. And actually, in the literature, they say that this has the benefit of, you know, improving a lot the computational complexity of your model. So you have huge gains in terms of efficiency and, you know, time needed to compute the model. So you can also use, I don't know, more pixels, or, you know, like use a longer time series in your analysis. So those are the results. So the first one is actually, well, is pretty dummy, I guess, results. So it's like just testing how our model is predicting the next day. So you can see that in the first picture, there's a good overlap between the mean over the whole sample predicted. And sorry, this is on the the independent data set, so the test data set. So for the years end of 2018 till beginning of 2020. And you can see also, I mean, good correlation between the predicted and the real data set. And you can see also how the root mean square error is distributed spatially. And actually, you can see already here in the yellow color of the third picture, the model seems to struggle, especially in the greenest areas. So this is like mountains and, you know, like forests and so on. And this is the result instead for the prediction 4 days ahead. And you can see that now the model is struggling even more in those greener areas. So you can see it here and also here. Yeah, correlation and root mean squared error. Yeah, if I show you pictures of, this is again 1 day forecast, and you can see that they look quite similar, especially, you know, see quite a good overlap on the violet areas. Those are the green, the very green ones, like the very green DVI. Instead, when you go to 4 days, you see that the model struggles here compared to here, right? So there's like less ability to predict that those are particularly green areas. It's also important to say that we probably have not chosen the best test set, because like those 2 years were particularly green. So it's like also, you know, like we have trained our model, like, I mean, it was kind of not an outlier, but, you know, like behaving quite different from the previous years, from 2005 to 2015, which were years where there was like an intense, like there was a series of intense drought events. And yeah, so this is actually the validation metrics. The first one is just if we use the NDVI from the previous day to predict the NDVI for the next day. And you can see that right now our model is actually beating that persistence baseline. And those are the results for 4 days, 7 days. What we aim to do here is actually to extend those predictions, as I said before, at sub-monthly scale. So being able to, you know, predict something reasonable at 15 or 1 month ahead. Yeah, so basically those are the next steps. As I said before, we will test other, test the the graph convolution neural network approach. We will also actually experiment with other precipitation products. So also to test the differences between different precipitation products, and include other variables that might really make sense and, you know, improve the model forecasting ability. So yeah, also some recommendations. So just from the preliminary analysis, it seems that it's possible to use satellite data at the least scale to perform accurate prediction of future vegetation condition, and also to perform drought analysis in general. So also if you want to see something different from the seasonal scale, if you want to see the evolution of those events, at sub-monthly scale, it seems that like exploiting geostationary data is a good way of doing it. And also the fact that, we can use deep learning algorithms to do this kind of analysis. Especially, I think those algorithms are really useful when you have high temporal resolution data, so kind of big data approach. Of course, we all know that the spatial resolution of those instruments is not good as other instruments, but of course, like depending on your application, for example, in our case where we wanted to do a prediction over a large area, it was particularly useful to use pictures from Severi. So that's it. Thank you.
Thank you, Riccardo. Nice talk. Very interesting. Are there any questions about this talk? Please. In the back first, and then we'll come up front. Thanks, Wolfram.
Thank you for interesting results. Just one question about why you have chosen ERA5, because it's a reanalysis model over this region. It was reason behind that. The second is you have used a supervised deep learning machine learning method. And why have you checked the time series that you have chosen? Because the time series is available from 1979 or something like that. Have you checked that if you take this time series because of the event that you showed, maybe you are underestimating, overestimating your prediction of the future? Because if you have many drought events only in this time period, maybe your model learn something that in a long time period is not the case.
So that's actually the point I was trying to make. So the ability of the model to generalize given the data set, probably, I mean, I took like the kind of different years as a, well, I mean, I did it to have like an accurate time splitting in order to avoid like data leakage problems, right? So just for this application, like this experiment I'm showing to you, I just wanted to point out, well, yeah, the ability of the model to generalize in case you have like such a variation, like such a green variation was not good given the training set. The usage, like the reason to use, well, like the radiometer, like Severi is active since, you have images from 2004, 2005, right? So of course, this is due to the limitation of the data that we have used. But in the future, as more data comes in, like you will be able to make more model that is able to generalize more. For the first reason, like ERA5, just because it's a reanalysis product, so it's good to make analysis back in the past, so to see. But actually, to be honest, we have exploited all the products that you have out there, so satellite, rain gauge, and so on. So actually, like we're gonna like the next phase is to compare the results from ERA5 with all the other products. Yeah. Thanks.
Thanks, Payman. Great question. Thanks, Riccardo, for the answer. Okay.
Yeah, Wolfgang Wagner from TU Wien. Well, I agree that it's of course very important to have very good time series. But what's the meaning of like having a one-day forecast, particularly if the data that you're forecasting is noisy?
Right. So, well, the meaning of one-day forecast is just to validate, right? So to validate that the model is doing something sensible. So, I mean, of course, I'm showing it to you now as a preliminary result, but just to say that the model that we have trained is doing something is not
the model that you will train for doing a longer-term forecast, which is what we need, will look different.
Right.
So every model that you do for every time step will have particular features. So I'm not sure what the purpose of this is. And again, like the experience that we have from using NDVI data, they're often very noisy because for many reasons. So again,
well,
I think
the objective
or looking at longer time series, then it becomes a useful exercise.
So actually, so there are, well, so the thing is, like when you use short-term data, you're able to see some patterns and some events that you're not able to see at other scales. So monthly, seasonal scales, it's different from. So for example, this kind of event if you use, for example, I'm talking about precipitation, if you see this kind of event, which happens in the middle of the harvest season, you cannot see it with the monthly data because it's going to be, maybe you're going to see a small variation, but you're not going to see like the actual thing happening, right? So the point I'm trying to...
Arid regions, vegetation can respond very quickly. Like a day is very fast.
Right. No, I mean, depends also on the kind of land, right? So depending also on the surface, so they have different responses also. So, I mean, different phenomena. I mean, of course, like probably depends on the application also, right? So if you're thinking about, helping people, like famine crisis, those are, well, maybe seasonal scale is good, but also, like to have a quick reaction is also helping this kind of like assessing where the is need, for example.
Great, Ricardo. Great answer. Thank you very much. All right. So because of time, I think we should move on. We have a few minutes for a group discussion. And the point of that discussion, I think we should really maybe just talk, even ask the speakers, a question or something like that. I thought I might go up here and grab these microphones because just get in the audience. We're going to have coffee after this, so be patient. Can I give this to you? And then if questions come up for the speakers, you guys just... Yeah. And so just maybe to kick it off, and we had some seed questions we talked about, but I think a lot of the talks today talked about quantifying the value of a future mission of a new satellite or a new technology. So we saw from Ilias, 2 pair versus 1 pair. What's the gain in uncertainty reduction? We saw with the GRACE thing how we can have this other band and then we can see more clouds. We saw with the from Andrea, the AWS mission, what is the value of this? And then from the machine learning approaches, Daniele and Ricardo, guys, I was just speaking to you about your talks that you add in observations into a machine learning approach, and then you can quantify the value of those observations. So a theme, it seems, for this session is the value of information that comes in new missions, new observations. When you're in a machine learning framework, you're introducing different pieces of information. Do you quantify the value of new pieces of information? What do you guys think, as the speakers, and you could pass the mic around, is the best practices or meaning of quantifying the value of new observations? Could you comment on that from your perspective? Thanks. And then I'll pass it to others.
Maybe I start?
Yeah, please.
Well, yes, absolutely. So in fact, this is when I say that, I mean, to assess that, because you have a new mission, you have 2 tools. I mean, from the spaceborne perspective, is what we are trying to do with simulations. So we are doing essentially simulations of these new observations, and we are basically trying to run retrieval on synthetic data sets, essentially, which actually in our case are built on, since we are thinking about the polar mission, we are actually using data sets built actually on the A-train, which is exactly another polar mission with the same kind of observation geometry. On the other hand, if you want really to assess these things, you need to have field campaigns. So that's where the ground-based measurements come into the picture, because in that case, of course, you have the radar, you have the multiple frequency radars looking upward, for instance, and you have some in situ truth. So you can establish really whether or not adding a second frequency helps in narrowing down the uncertainties in the microphysics. In our case, the microphysics is the size, is the amount of the mass of cloud, is the dimension of the particles. So in that case, you can establish whether or not indeed the second frequency helps. So this is my view. You need to do both.
operational system?
Well, it is possible to quantify exactly the quantity of information, but what we do is to assess the impact of this new information more than quantifying the information. So there are two sides. You need an information, and you need to use it. So to have a proper model that can extract this information from your data. The approach that I prefer is the big data one, in which I put everything inside the model. I throw the machine, and then I have the impact of these results, with or without the new input. But let's say that with new information, what you can get, the real value sometimes is the new insights of your physical process, of the physical process you are observing. What we can see with the new channels of AWS is that we can see different things that were invisible before. So the observation of supercooled liquid droplets is something like that. And that's not something that it's possible to be extracted with automatic processes such as neural networks and big data. It's something about process, new process, study of case studies, and it must be also supported by field campaigns, because that's where you understand processes.
If I may add on going back to the impact of the assessment of the impact of future technologies, what we're trying to do at ESA, especially when designing the next generation gravity mission, is to perform very realistic simulations and benchmark them against real processing of the current GRACE mission. So it's important to always benchmark it, because in our case, the campaigns make less sense. You cannot really make a campaign to validate or to go towards to the signal that you want to improve. So we really have to take care on benchmarking the synthetic experiments in a good way. Yeah. And then quantify, and then really we go back to the user needs, the international user needs, and see where we are in satisfying the user needs, because we have really all the feedback we have from the GCOS and the climate variables, that there are specific requirements that, of course, are very demanding, cannot be satisfied by only satellite observations. You have all the kind of means to satisfy them. And we go back and see and trace where we are with the new mission.
Benchmark towards, what's currently available, so the state of the art. So let's say CloudSat versus or GPM or something, right? We say, okay, what would GPM see in the same situation, and we see the difference, we see the improvement.
So there's kind of an implied user need in what everyone's doing, right? And you're saying, how well do we achieve that objective of fulfilling our end user need, right? For operational stuff, of course. In Ilya's case, it's very explicit end user needs, right? That are specifically listed and defined, and it's quantifying those metrics too, right? So different approaches. Rajan, did you have a
I had a question or a comment. We are in this session, we are talking about the value and impact of different hydrologic variables for our different applications. The last presentation we heard about some of the stuff for drought, and you looked at precipitation and NDVI, but precipitation only has no memory. It gives you only instantaneous observations of water availability. Essentially, agricultural drought in general is defined as deficit of water uptake available for the plants. Why didn't you consider variables such as soil moisture or groundwater, which are the ones which have the memory and are essentially being the variables which the plant uses for uptake of water? I think it's important to consider the critical variables, because we are going to be doing studies coming to results without accounting for the key hydrologic variables otherwise.
Yeah, so as I said, those were preliminary analysis, and actually the next step was, to include soil moisture in our analysis. So the reason why actually we focus first on precipitation is actually because we come from an institute that works on with precipitation. So actually that's the reason why we focus on precipitation first. But yeah, you're totally right. Like those will be the next step. So, but that's why actually I was presenting preliminary results. I was not, presenting. So, and actually, well, my research is more into artificial intelligence. So also, like looking at, like capabilities of different algorithms and see how, but also to be honest, like on the literature that I've seen, they also do this kind of analysis, like trying to compare correlation between precipitation and vegetation, which I totally agree that it's not like the good way of doing it. But yeah, as a baseline, we had some studies like in literature that were doing this.
Thanks.
I may follow up a seed question here that we have, where I just want to address this question here in the room, because we have a session about the future of water cycle research, and I want to have some input on the what is, according to your opinion, limitation of the current Earth observation systems there that that need to be pushed to go closer to improving the water cycle research in terms of closing the water budget and so on. For example, we saw specific presentations. We have machine learning tools. We have the new type of observations. Where do you think in the water cycle research this contribution contributes to?
Yeah, it's a great question. There's ways to think about it, like, do we need entire new technologies to observe things we're not observing? Or is it always a matter of increasing resolution and increasing temporal resolution, spatial resolution? Or are there hydrologic variables that are just not well represented by remote sensing? I mean, snow pops to mind, right? So it's really, really hard to observe. But any thoughts from the room on any of those things? Priorities in your minds, your personal, yeah.
To be quick, increase temporal resolution, and if you want to go operational, the latency of the data, also of high resolution data. So for instance, Sentinel-1 still is not available for some application in a short time. So the time, because everybody says always to space, but in space now actually we have very high resolution from several platforms, but in time, and most of the hydrology processes basically have a very high temporal variability. Precipitation is the first, but not only.
And Luca, for which variable you think this is the most important?
Precipitation for sure, but also soil moisture then, but actually soil moisture probably I'm biased. And river discharge for sure. So river discharge every 10 days, 20 days, probably it's not really, it's good for science, but not for any kind of application. It's small basin. A small basin means even basin larger than 300, 400 square kilometers. So they are not really small. They are the basin in which basically we have to make predictions.
Daniele, do you agree that latency is a big obstacle? Is it?
Daniele, yes, I agree. Latency is very important. We for operational products, of course, for operations, less for science and study, past case studies, but yeah, for operational hydrology, latency is very, very important. We have some hours for this latency for these passive microwave instruments, kind of 2-3 hours. So in order to make the precipitation rates products for real-time monitoring, we need also to make some near real-time forecast soon in order to fill these gaps.
Are there any hydrologists in the room that want to go on the record as saying that their variable is underrepresented, or they'd like better observations of a specific process or variable? Yeah.
I'm a meteorologist, so I can just agree with Luca. So it's really temporal resolution. It's key. So you for everything, for precipitation, of course, but even if you want to do the flooded areas, we know that it's just over a couple of times that you see the updates, and so it's critical. I agree. Just to stress it.
Yeah.
May I add something? No, so I'm also kind of from meteorology, and of course I'm more involved in clouds and precipitation in the atmosphere. So if you want to improve the modeling and the forecast of precipitation, you need to improve the representation of clouds in models and cloud processes in models. So that's still a
underrepresented process.
Yes.
Clouds, yes.
Yes, and you need, as I said, I still believe that we need more radars, more multi-wavelength radars, more capabilities there.
Yeah, yeah.
Then in terms of variables, we don't know anything about water under the ground and how much water we are using. These two tasks should be addressed. Whoever is able to do this, which satellite model, whatever, would be very nice.
Some people are working on this with gravity, obviously, and in INSAR, but it's still the beginning, still new research. Sure.
So in terms of one of the things that is really missing from a water budget or hydrology perspective is anthropogenic impacts, the human impacts like irrigation, how much water is being used for irrigation, we don't know, or we don't have that type of information because that's a huge component of the water cycle in especially agricultural domains.
Yeah. Very good point.
Some interesting work happening in different groups on trying to estimate irrigation using different techniques, soil moisture for one, but other techniques as well. So it's definitely an open, seems like a future field. Elias, what do you think?
I think that for the last point, important is not only temporal resolution of existing techniques, because I'm talking about existing techniques, but also spatial resolution and uncertainty. There you get to see more features, local features, for example, that are a bit not so well monitored.
Yeah, for sure. Yeah, especially for gravity, which is traditionally
I'm thinking with this background in hand,
technique, that if we can enhance the spatial resolution, there's a lot of thresholds and applications for more aquifers that can be observed and higher resolution processes for sure.
Yeah.
Just to comment on the relation between temporal and spatial, I've just to order it, and I would put temporal first, then spatial. Although, of course, if you can go to better than 6 kilometers or 5 kilometers, 2 kilometers. But the thing is that you have high uncertainty in model forecast still. Just for today, we were not sure where it's going to rain more here in Portugal. So you don't know in which basin it will be, which of the basins will be affected. There are two more in risk today, more to the center of the country, but are you sure about which basin is going to be affected? So you have uncertainty on the model forecast. So with the resolution that we have, we kind of solved that basin dimension. But it's with temporal, that's when you, in a nowcasting perspective, in real time, really need this information to really tune the area.
I think this goes into the perspective of, for operational services, you need definitely to have higher temporal resolutions for nowcasting and so on. When you think about more scientific purposes, you need also the other two, what I mentioned. Of course, it's not black and white.
You had this presentation for the precipitation on the warm, let's call it warm precipitation, with the lower part of the troposphere being covered. So I think that you mentioned you said that it will be covering the whole thing. So I think that in the technical part should be something, because we know that it's underestimating. It's the actual capabilities are not covering this part. So clearly, this would be one of the ways. Seeing it from a meteorological point of view.
Any final thoughts, comments? Speaking of latency, there's coffee outside, and we're a few minutes behind schedule. But,
We're a bit late.
thank you, everyone, for a good discussion, and
Thank you very much.
Yeah.
Great talk. Okay, so this is our first presenter then.
Yes, yeah.
Hi, Wolfgang Wagner.
Yeah, nice to meet you.
Good.
Yep.
We said anyhow we start a little bit later because the last session was over.
Okay, no problem. Yeah, yeah.
But now he runs again.
Yeah, well,
yeah, well.
actually, I like to grab another snack.
Maybe we go out and chase some few people. I'll do so. I'll do so. I'll go with you. It's fine.
Okay.
So very good that people start coming in from the coffee break. So we said we start a bit later because also the last session was a bit longer. So please let me quickly introduce ourselves. So my name is Wolfgang Wagner from Technical University of Vienna, and my co-chair is?
I'm Francisco Peña from Stockholm University.
Yeah, so we have 5 speakers today, and the first one will be Tian Hu, and he will be presenting his work on the terrestrial evapotranspiration. You have, in total, we have 20 minutes, and it's up to you to how long you go,
Okay.
how much discussion you would like to have.
Yes, okay, thank you. So, hello, my name is Tian Hu, and I work at Luxembourg Institute of Science and Technology. And today my topic is about high-resolution mapping of terrestrial evapotranspiration using ecostress, and through which we hope we can provide some insights into the surface edge balance modeling for the future thermal missions. So we know that, the surface edge balances, or let's say evapotranspiration is a very important component in the terrestrial water cycle. And here we use a very simple conceptualization of the surface edge balance, like this diagram to describe this process. So in this process, there are 3 important components in our conceptualization. So the first one is the net available energy. This works as the engine to drive the whole system. And the second one is the atmospheric water demand, which is the demand to drive the water from net surface to the atmosphere. And the third one is the soil moisture, which provides the fuel for this like water loss from the net surface to the atmosphere. So on the right-hand side, you can see two like Diode cycles. And the first one is a Diode cycle of radiation and evapotranspiration over a very humid biome. And when it comes down to it is the like the Diode cycle of radiation and evapotranspiration over a very arid, very dry, water-controlled like biome. We can see that for the humid ecosystem, the symmetry is really good for evapotranspiration. But when it comes down to the arid region, we can see that there's a very marked like asymmetry between the radiation Diode cycle and the evapotranspiration Diode cycle. This is because of the like a huge or substantial water stress in this kind of arid biome. So that means we need to describe this kind of water constraint in the arid or semi-arid region to quantify the evapotranspiration accurately and with low uncertainty. So in this kind of scenario, that's how like the surface temperature plays a role in the surface energy balance modeling. That's why we need thermal infrared remote sensing to retrieve the surface temperature and use the surface temperature as a proxy of surface water stress to drive the surface energy balance process. So we just mentioned that thermal infrared remote sensing is quite efficient and also effective tool to retrieve the surface temperature. So currently there are quite a lot of sensors where we will provide thermal observations, and from which we can retrieve the surface temperature, including polar orbiting and geostationary. But for polar orbiting, normally it has relatively, let's say, coarse temporal resolution with relatively high spatial resolution, and for geostationary satellites is the opposite. But in 2018 we have another mission that is ECOSTRAS on board the International Space Station. This is a pathfinder for the future thermal missions. And it has a spatial resolution of 70 meters. At the same time, it has a relatively higher temporal resolution with a revisit frequency between 1 and 5 days, and also in the contiguous US continent. I mean, over some specific sites, they can provide several revisits during the course of the day. So as I said, I mean, this kind of Explorer mission, ECOSTRAS, can provide very good preparation for the future thermal missions, including like Trishda from CNES and ISRO, is collaboration between India and France, and also SPH from NASA, and also LSTM from ESA. So, but combine these three future thermal missions together, we expect that in the future we can get like around 50 meter spatial resolution, and with a daily revisit time, like LST temperature, and then subsequent ET retrieval. So this is the to prepare for the future missions. Then we have this European EcoStress Hub project funded by ESA. So we just finished the phase 1 in 2022. So in this phase 1, we targeted at comparing different altitude algorithms and ET models using EcoStress observations and with homogeneous ancillary data. And then we just started this phase 2, phase 2 this year, and we'll have several scientific objectives in this phase 2. And the first one is to investigate the sensitivity of surface energy balance and components to the surface temperature. And second one is to upscale the instantaneous ET to daily scale, because we know that the orbit of EcoStress is very special because it's asynchronous. It's very different from the polar orbiting or geostationary, so it is quite tricky. And that's why it's to carbon the surface energy balance process with the couple the surface energy balance process with the carbon cycle. And in total, these two phases we expect that it can contribute to the preparation for the future thermal missions. So for the LST and ET data generated in the phase 1, they're all available on the WASD platform, which can be downloaded and play with if you have interest. So here is the link, and here's the QR code. Yeah, you can check it out if you are interested. So this is the evaluation of LST in our phase 1. We can see that, I mean, actually, but we have to mention that we just use 6 sites to evaluate LST because of the limitation of high quality LST, institute measurements. We can see that actually the split window and TS algorithm, which are the two most widely used LST algorithm in the thermal community, actually perform quite similarly. I mean, and also as compared with the other state-of-the-art high spatial resolution thermal missions, let's say NanoSat or ASTA. I mean, the LST retrieval accuracies are also very comparable. So this is the ET evaluation results for in the EH1. So in EH1, we implemented 3 different models with contrasting structures. The first one is an analytical model. It's called STIC, developed by Dr. Kashgar Malik. And the second one is a one-source parametric model. It's called SAPS. And the last one is a two-source model, also a parametric model, TSAP. Okay, I mean, we use 19 sites over Europe from EFTC and ICOS. At covariance size, we can see that as so as compared to the SAPS and TSAP and these 2 models, I mean, the performance of STIC is relatively better in terms of RMC, bias, and correlation coefficient. And also, we can see that, I mean, in a lower panel, we can see that when it comes down to the very arid, very dry area, I mean, the advantage of STIC is more obvious as compared to SAPS and TSAP. You can tell from the greater KGE value as compared to those of the SAPS and TSAP. This is comparison between STIC and the PDJPL. We use the same eddy covariance size over Europe. I mean, 19 size over 6 different biomes, and we put them together. You can see that, I mean, in terms of all the 3, uncertainty metrics, I mean, STIC is relatively better in terms of RMC, bias, and correlation coefficient. Also, especially in the very dry region, let's say savanna, you can see that, I mean, the PDJPL model is relatively, what should I say, I mean, the overestimate ET because of the very loose LST control. So, I mean, the STIC model performs relatively reasonably over this kind of water-constrained region. So after we finish the EH phase 1, then we start to question ourselves. So for the future thermal missions, for sure, there will be more than 3 bands available, thermal bands available. And then we can implement, let's say, either SW, a split window, or TS, temperature emissivity separation algorithm. But which algorithm we should go for to have, more accurate LST retrieval and then subsequently more accurate ET retrieval? Probably, I mean, some people say, wow, it's quite simple. We just evaluate LST directly. But actually, this is not such a simple task because there are quite some challenges on the way to evaluating LST. The first of all, because we know that as compared to the eddy covariance size, I mean, the high quality LST measurements is limited. Just as mentioned in our EH phase 1 LST evaluation campaign, we just use 6 size because the limitation. And the second, what should I say, hurdle on the way is that, I mean, normally if we use the long wave radiation measurement from pure geometer to evaluate LST, but the signal actually is different from the directional signal observed by the satellite, because we know that the pure geometer is observes the long wave radiation, which is hemispherical and broadband, but the radiometer it observes a directional signal. So it's kind of like there's some, what should I say, discrepancy between these 2 signals. And last one is like currently still there's a lack of direct comparison of ET retrievals using different LST estimation algorithms. So this is first the research question. And the second one is like, actually how we should incorporate LST information into the surface added balance pulses, because we have like analogy. I mean, there's a trinity 3 1 1 3. So like including aerodynamic temperature, aerodynamic conductance, and canopy surface conductance, and how we can and where we should incorporate LST information into this kind of trinity to represent the surface water stress, and how at the same time, meanwhile, we describe the interaction among this among the trinity. So this is the research question. And just bear this kind of 2 questions in mind, and then we have this kind of analysis. So we did some sensitivity analysis in terms of LST impact on ET. So we selected 19 sites over Europe from ICOS and EFTC, covering 6 biomes. And then we use SW-LST and TS-LST to drive the STIC model. And then we retrieve different ET estimates as well as the trinity, the 3 parameters. And then we compare how these 2 different LST, influence the final ET retrieval and the trinity parameters. So here, the first column is the the ET estimate from TS algorithm. The second is the result using the SW-LST algorithm. So we can see that actually over cropland and grassland, I mean, the accuracy using TS and SW are very similar. However, when it comes to the forest, which is a densely vegetated surface, I mean, the SW has a relatively lower bias. So this is due to, we infer this is due to the like emissivity setting, because we know that, I mean, over forest, the emissivity spectral contrast is really, really low. So which will hinder the performance of TS algorithm, which, you know, I mean, this kind of emissivity spectral contrast is very important, but it doesn't work so well for TS, but it works quite well for SW. So for the other three biomes, shrubland, wetland, savanna, I mean, shrubland, wetland are also very similar for these two LST retrievals when they drive the surface edge balance process. But when it comes down to the savanna, which is very dry biome, we can see that actually the TS algorithm performs much better as compared to SW. This is because of the very high spatial heterogeneity of this kind of landscape. Because we know that in the SW algorithm, the emissivity is treated as a priori. Normally use a background soil emissivity, and then we just incorporate some vegetation information into this kind of process. But we know that the vegetation information cannot be obtained timely. Normally it's 8 days or 16 days. You cannot reflect the seasonal variation very timely, and also this kind of because of the spatial mismatch between ancillary vegetation information and ecostress, there could be some spatial heterogeneity that cannot be captured by this SW algorithm. But for TS, the temperature and emissivity are estimated simultaneously. So this kind of spatial heterogeneity can be reflected quite clearly in the process. That's why the TS, the ET retrieval using TS LST has a better performance. And also we can see that as compared to the other biomes, the other 5 biomes, the sensitivity of ET to LST over savanna, where on this kind of water constrained biome, is really high. It also, what should I say, confirms the significance of temperature in ET retrieval in this kind of water-constrained ecosystem. So this is the sensitivity of neutrality to dense surface temperature. So the first column is the sensitivity of aerodynamic temperature to dense surface temperature. The second one is the surface canopy conductance. And the second one, the third one is the aerodynamic conductance to dense surface temperature. As compared to we can see here, as compared to the aerodynamic conductance, the surface canopy conductance is much more sensitive to dense surface temperature for all the biomes, let's say for forest, cropland, grassland, and also when it comes down to the shrubland, wetland, savanna, it's all the same. That means actually, the stomatal conductance is more sensitive to dense surface temperature as compared to the aerodynamic temperature. Is quite important information, and especially when it comes down to the savanna, which is a water-constrained biome. You can see that both the conductances are more sensitive to dense surface temperature as compared to the other biomes, including surface canopy conductance and also the aerodynamic conductance. That means, again, it confirms the what should I say? The control, the serious control of the surface temperature on the surface edge process in the water-constrained biome. So this is a comparison between the surface temperature versus and with the aerodynamic temperature. Because because the aerodynamic temperature is quite important in this process. But how can we normally we use some parameterization method to approximate the aerodynamic temperature, but how exactly they correlate to each other? So we did some analysis. So we can see that for, let's say, for forest, actually we can see that for most samples the aerodynamic temperature is above the radiometric temperature. This is because there's normally the water stress is rarely, but it's not everywhere nowadays. Also in forest, there could be some water stress, but in general, the water stress is relatively low in the forest biome. So that the evaporative cooling can play an important role to cool down the radiometric temperature. So in this sense, the aerodynamic temperature is always above. In most cases, not always. In most cases, above the radiometric temperature. But when it comes down to the savanna, let's say the last column, we can see that for most let's say 90% or 80% samples, the aerodynamic temperature is below the radiometric temperature. That could be some interaction. There could be, let's say, two factors. One is the fractional coverage, because we know that over savanna, the fraction coverage is pretty low, so that we can see more bare soil. The temperature of bare soil is relatively higher as compared to vegetation. And also because of the enormous water stress in this kind of water-constrained ecosystem.
4 minutes.
Yep. So the evaporative cooling cannot, work so well. So that it just lead to the result that the radiometric temperature is higher than the aerodynamic temperature. So for savanna, we can see that there are some dark points. That means it's very dry. However, still the radiometric temperature is below the aerodynamic temperature. That means water stress is important to decide its relationship, but there's not all the story. I mean, the fractional vegetation cover is also important to decide the relationship. So here we just analyze the slope between the two temperatures with different factors. Let's say FEC, soil moisture content, or VBD. We can see that the soil moisture is the most dominant factor to decide the relationship between these two temperatures. Also, the vegetation coverage is also important, but not so dominant as compared to the soil moisture content. So so here's the conclusions. The first is about length of temperature retrieval algorithm. So we can see that overall, the SW and TS have very similar accuracies. However, the TS shows advantage over surfaces with high spatial heterogeneity and seasonal variation. In contrast, SW performs better over densely vegetated surfaces. And second is about the relationship between land surface temperature and aerodynamic temperature. So we can see that the relationship is influenced by vegetation coverage, but dictated by surface water stress. And also we can see the relationship varies across different biomes. That means there's no universal equation which can be used to convert LST into aerodynamic temperature. The last one is about surface edge balance modeling. We can see that the high sensitivity of conductance is both conductance to land surface temperature over water-constrained ecosystem. That means, over this kind of water-constrained ecosystem, land surface temperature is very important to drive the surface edge balance process. And also, a surface edge balance, surface calorie conductance is 3 times as sensitive as aerodynamic conductance to LST of all the biomes at least. And next is some implications for the future thermal missions. The first one is about LST estimation. By combining TS and SW algorithm, it's advisable that we should select the TS as the primary LST retrieval algorithm. But at the same time, when it comes to the densely vegetated surfaces, we should switch to SW. And the second one is the market significance of LST for ET estimation over arid and semi-arid regions. So that's why this is the meaning for having the future thermal missions. And last one is about ET estimation. So through this kind of analysis, we understand that both conductances are very important in the surface edge balance process. We should not bypass one conductance to drive this process if you want to get more accurate ET retrievals. So this is a shameless advertisement for a postdoc position at our institute. And we have a 2-year postdoc position in Luxembourg at our institute, which is targeted at working on the thermal infrared remote sensing. Basically, more specifically, is on NS7 temperature and evapotranspiration retrieval from high resolution thermal satellite emissions. And if you are interested in this position, feel free to reach out. And this is my email. So we are welcoming you to Luxembourg. So thank you. That's all.
Thank you.
So I'm happy to take any questions if I have time.
We have time for one short question. Well, maybe then from my side, you said also in the title, insights for future thermal missions. From the insights you're having, what's the implications for future missions?
Yes, just like what I said here, this is the implication for the future thermal missions.
Yeah, but what's the impact on the design of the satellites?
Yeah, for satellites, for the design or manufacturing, we couldn't provide too much insights, but for the LST retrieval algorithm,
for the algorithms, okay.
Yeah, for algorithm and methodology development part, yeah, we can probably contribute, if the analysis is beneficial.
Okay, thank you.
Thank you so much.
Then we move over to the second presentation. Unfortunately, Martha Anderson couldn't make it, and Yuan Tuang was so kind to jump in and give her presentation. Again, on evapotranspiration on a global scale.
Hello, everyone. So I'm not Martha Anderson. I'm Yun Yang, the second one here. And also now I'm with Mississippi State University Department of Forestry. But before I joined Mississippi State, I've been working with Martha for a long time. I will give her talk. Both Martha and Bill Kustas, they were very much looking forward to come here, join the meeting in person and meet all of you in person, but they couldn't make it and need to change this at the very last minute. So I will try my best to cover the slides, and I will also try my best to answer your questions at the end of this. So the title of this is a global multi-scale ET mapping system using multi-source thermal imaging. So there's a really good consistency between my talk and Tian's talk. So first, let's talk about our modeling system. Our modeling system is also is based on the two-source energy balance model, which Tian also mentioned. And the two-source energy balance model, it partitions the radiometric temperature into the soil component and vegetation component. So we can estimate the soil and vegetation fluxes independently. And also combining this TSAT model with the atmospheric boundary layer condition model, we can estimate evapotranspiration at regional scale, which is about 4 kilometers, and we use geostationary land surface temperature observation for this. So this is the first part, which is the Alexi model. And for a lot of applications, that 4 kilometers is too coarse, especially for agriculture. You want to look at the condition of each field. So we want to get to a finer spatial resolution that can directly use it for a lot of applications. So the way we do it is we disaggregate the fluxes we get from Alexi and using this Alexi. So with this Alexi, we use OST input from satellites with finer spatial resolution. For example, we use Landsat, WIRS, Sentinel-3, and UAV data. That like now you probably feel, okay, so why you have so many different data here, right? So it's just for the dysalexy part, when you fit this model with different spatial resolution, you will get ET estimation at different spatial resolution. And of course, along with different temporal resolution. So with all these different sources of satellite data, we can really mapping ET over a wide range of spatial and temporal resolution. And using geostationary data, we can estimate continental regional ET estimation. And with MODIS, WIRS, we can have daily about 500-meter ET estimation. And with Landsat, we can have 30-meter ET estimation. But when you look at all these data, they all come with very different temporal resolution, especially for the fine spatial resolution. For the fine spatial resolution we want at the Landsat scale. This is the scale that you have least thermal sampling frequency. So what we do here is we want to use all of those together, and we feed all these into this data fusion system. So combining all this, we can get a 30-meter daily ET estimation. And so here you can see, although we can use this data fusion method, but the fused results a lot of times still depends on the image at the finest thermal observation in your system. So this thermal image, like LST, is a critical input for the energy balance model. I'm going to show you one example to demonstrate why the thermal image is so important in the ET estimation. Okay, For OpenET, OpenET is a project that we have in US. The goal is to provide this field scale ET estimation to the end users, stakeholders, and we provide this user portal. We also provide API for users to download the data and use the data for their irrigation scheduling and water resource management. So inside of this OpenET platform, we have 6 different models. And these different models, some of them, they highly rely on the energy balance here. And some of them, they highly rely on the crop coefficient, which is the vegetation indexes. And this provides us this really good platform that we can compare how these thermal-based model and the vegetation index-based model works for ET estimation. So let's look at these field in the center of this image. So this is a double crop field with winter wheat and corn. This is a field in the Central Valley of California. So when we look at the time series ET estimation from the thermal-based method and the vegetation index-based method, you can see between these 2 crops, the figure here, like the curve from these 2 different methods are very, very different. And let's just move to the spatial pattern here. So this is in the center, that's the field we want to highlight. And this is from the energy-based model, the ET estimation. So there is a irrigation happening, although it's between 2 crops. And normally people has a pulse of irrigation to flush out the salt from the field to prepare for the second round of crop. So you can see the thermal image can really capture the signal. But when you look at the vegetation index-based method, they totally miss the signal of irrigation, and there's just no ET, very low ET there, because at that time there's no vegetation. Right? So if we based on vegetation index and there's no vegetation, you just cannot capture that ET signal, which the thermal images can capture that. And when you look at the entire region in this screenshot, actually you can see there are many of these fields are having the same condition that, it's a double crop and it's right between the transition from one crop to another crop. So when you want to look at seasonal water use, and the thermal image signal really provides this accurate water use estimation. So this is how important the thermal is. And now we highly depend on Landsat signal because Landsat has both the thermal observation and also the vegetation index that we also need in the model. But we all know that Landsat has a relatively long revisiting time. It's 16 days for one Landsat. And now with Landsat 8 and 9, it's about 8 days. But still, for agriculture applications, you can miss this critical crop condition. And when you consider the cloud contamination, for those cloudy area, you may just don't have even one image over a month. So we really have this limited fine scale thermal sampling. And how we want to solve this for now is we want to bring in the other thermal observation signals here. And one we are working, we have demonstrated in our system is the eco-stress that Tian also mentioned. So we also use WIRS. WIRS also has this daily coverage of global and also 375 meter thermal signal. So we use all of these together in our system is this data fusion system. And when we first look at this, when you put all these inputs together, like this is from Landsat thermal, this is from eco-stress thermal, which is 70 meter, and this is WIRS, this UNCORS, it's 375. So how we can use all these together in one system, right? And the first thing we want to do is we want to keep all these thermal inputs consistent first. So how we do it is we use a data mining sharpener method that we sharpen the coarse resolution of OST into a finer spatial resolution. The theory behind this is just build the statistical relationship between the spectral bands and the thermal bands. So the spectral reflectance has a higher spatial resolution. So that can help us to sharpen the thermal information. So after apply this, we can see that the native resolution thermal observation, and this is our sharpened land surface temperature. So now we are ready to use all these in our system. But this doesn't mean we don't need more thermal observation at fine resolution, because this sharpening method has limitation. You just cannot sharpen anything you want, especially when the native resolution get too coarse. So you can see when we test it from 120 meter all the way to almost 1 kilometer, and we look at this field, this detail is getting, it's just losing this detail. It's because in the native resolution of the thermal image, it's just already know enough information that you can use to sharpen it to enough detail that can really recover that spatial resolution. So although the data sharpening method can help at some level, but we still need a lot more fine spatial resolution thermal observations. Okay, so with this system, this data fusion field scale ET construction method, we already applied this to many primary agriculture sites in the US. And of course, there are also other places around the global. But here we want to highlight one study that we have done for many years, which is the GREPAX project led by Bill Custis, and is our first test beds in the vineyard in California for the deficit irrigation. So let's look at a detailed evaluation of how the model performs over these vineyard sites. Okay, so these are the comparison over different flux towers in that region. And here I want to just highlight something. For each of these flux tower, we look at this, the blue dots, they are flux tower observation. They are ground observation. And when you look at each of this figure, and the red line is our fused daily ET at 30 meter. So you can see we are really capturing the detail of the flux tower observation. And also you might not see it very clear that we also have the red dots is the Landsat overpass time. And also we have green dots and VIRS, and yellow dots eco stress. So we're really using all this information together to improve the ET estimation. So these are the vineyards that in the California, and we will focus now on one of these to look at in detail, because I know this is somehow too competitive to say. And this is the Reaper Dam site. Reaper Dam site is right out of the Fresno, city of Fresno in California. So now let's look at the detail of these plots. So this is one plot for Reaper Dam site from 2018. And again, when you look at this figure, the blue dots are flux tower observation, and the red dots, they are from Landsat. So you can see California is a sunshine state, right? So you don't really have that much cloud during the spring season, but you do see this raining spring season. So in the green season, we see many Landsat coverage because we're combining the use of two Landsat together, so we can get a good thermal sampling. And we also have the EcoStress. EcoStress was launched in 2018. And that was launched in summer, and we start to have data from July to September. Then the data come back again in 2019. So as you can tell, these red points are from the EcoStress retrievals. So you can see we are capturing this dip in the water use. And for eco-stress, even is just this short time period, it already gave us a lot of added value to improve our ET estimation. And the dip here actually is associated with the variation of the grape. When the grapes start to turn color, and for the management, they start to cut back the irrigation and to limit the vegetation growth, but help with the grape development. So we are doing a really good job to capturing that water use change here.
4
And
minutes.
also, when you look at this spring rains, we don't have that many Landsat observations, but combining the weirs, which are the green points here, can really help us to improve the temporal sampling here. Okay, so with all these different sensors, eco-stress, weirs, Landsat, they all go through your sites in different time of the day or in different days. So apparently, since they overpass at different time, you will see a very different temperature. So this is native, this is a sharpened OST. You do see the temperature range is different. But when you look at the daily ET estimation, it's very consistent. Somehow it's helped by disaggregate from the common Alexi flux. So they are very consistent here. And in some cases, because of the different overpass, we can actually learn a lot of these diurnal water stress differences. For example, Landsat, the overpass in the morning, eco-stress in the afternoon. And when you look at this field in the middle, for the afternoon eco-stress overpass, we have a higher ET. This suggests that they somehow irrigated between these two overpass time. So when we look at all these statistical metrics from using different sensors, Landsat, eco-stress, weirs, we can see actually Landsat always give us a relatively better results, although all of them are giving very reasonable results. The reason is that Landsat has a relatively higher native thermal resolution, and also it has a thermal and whisper band on the same platform. So that really helps. So this system, actually, we are operationally running this for the E&G Gallo 1 yard company in California. Our colleague Kyle Knipper at USDA ARS at UC Davis, he is running this, and he provides this weekly water use estimation to the company and integrated this information into their management dashboard to help with the irrigation suggestion for the entire 1 yard company. And for the larger region, we are using OpenET. So when we look at OpenET, these are the ET estimation from the thermal-based model. So you can see there are many different colors in this, green, yellow, green, and blue color. And this helps us to demonstrate some of the fields, they are really using this high stress deficit management. And some of them, they are using a lot of water. They are trying to establish these the young 1 yards in the study field. And when you look at these nice details here, and when you move to a vegetation index-based model, all these details actually start to lose. So you don't really see this detailed crop stress information from this vegetation index-based ET estimation. So let's zoom out a little bit to the global.
I'm really sorry, very nice results, but time is really already up.
Okay.
So try to wrap up.
I will try to go very fast. It's almost the end. So this is our effort of this global Alexi. So what we want to see here is instead of using geostationary data, now our colleague Chris Han at NASA Marshall, he developed this method using MODIS and weirs. So now we can have daily coverage of Alexi and also real time, which we use it to create this evaporative stress index that can be used for the geogram group. to monitor the drought and help with the crop watch condition. So this is the ESI map inside GeoGlam, and this is the crop watch results using our ESI product. This product is operationally produced by NASA, and you can find it on NASA disaster portal. And at the very end, we are trying to improve our thermal sampling at coarse resolution, because when you we are using microwave to estimate land surface temperature and under all weather condition. So you don't need to worry about cloud, because the long wavelengths of microwave can penetrate to the cloud. So this is an example demonstrate how like this, when you only use thermal sensor, this is how many % of days of this year you can get. The largest is 90%. And this is how what you get from using microwave data inside of your system. So we really see a lot of gains from integrating microwave. Okay, so, and also not just the frequency,
Please,
also the
finish.
data is cleaning. Okay, let's just skip this. So the future recommendation is when we see all these future like missions, SPG, Trishna, LSTM, and Landsat Next, what we think is important is it would be great if we could have a harmonized land surface temperature product. To harmonize all these possible sensors. And now we have the harmonized Landsat Sentinel, so we can build on this and harmonize it, and also the same for the global product. So with this, I'm going to conclude my talk. And thank you very much for your attention, and sorry for go over a little bit.
Thank you very much. Suggest that we could directly go to the next speaker.
Okay, so the next speaker is James Garrison from Purdue University, and he's going to talk to us about the hydrological remote sensing using signals of opportunity below 400 megahertz. Thank you, James.
Okay. Yeah, I'm going to talk about kind of a new microwave technique called signals of opportunity that's been a large part of my research for the last probably decade. Actually, if we go back to GNSSR, my entire career has been revolving around some form of signals of opportunity in the microwave. I'm going to kind of summarize a few projects that are ongoing. The long list of co-authors here, the ones at Purdue are my graduate students. I also have collaborators at Goddard Space Flight Center and JPL. First, I'm going to talk about the problem statement. Why do we want to go to 400 megahertz and lower, which is a very low frequency? You saw stuff earlier that was hundreds of gigahertz, so I'm going, decades lower than that in the spectrum. And the difficulties in using conventional radar radiometry at those low frequencies. And which leads to signals of opportunity. I'm going to talk, and this isn't really chronological order in how these things develop, but I think this is a logical way of presenting the kind of the current state of the art for signals of opportunity. So I'm going to talk about some sensitivity studies. A recent PhD student just completed, Sehel Kim, on the previous stage. He's now at JPL. Related technology development, and then technology is also got new sensors, I need new algorithms. So I'm going to talk about kind of the current state of the art of the algorithm development, which is still very much in a preliminary state, and that's going to flow down into my outlook and recommendations. Okay, so problem statement. Why do we need microwave frequencies to go to lower frequencies? Why do we need lower frequency microwave remote sensing? This is just a really simple penetration of a single layer of soil. So it's an ideal case. Air above, one type of soil below. And then I look at the penetration depth at two different soil moistures. So a low one and a high one. And then I go an L band here, and that's what, SMAP, SMOS, L band is kind of the standard for soil moisture remote sensing. And then we see at, at high soil moisture, we have, below 5 centimeters of penetration. At very low soil moisture, we can get up to, maybe 10 or 15 centimeters. Okay, so generally, L band and higher frequencies, believe it's sensing the surface soil moisture. Okay, but we would like to go down into this root zone, about where, a meter or so below the surface, where the plant roots absorb the water. I'm an engineer, not a hydrologist or an agronomist, but my understanding is, that's part of that cycle of where the water is taken from the soil into the plants going to evapotranspiration. So it can be estimated with data assimilation and various methods, but there's no really direct way of measuring it. Haven't said anything about the vegetation on top. Certainly, if that gets thick enough and you're starting to look at forests and those type of environments, the penetration through that media is also a concern. Okay, so why can't we just use lower frequencies? When conventional microwaves, there's kind of three problems in doing that. One is fundamental physics. If I have a diffraction limited measurement, so my measurement's defined by my aperture, it's proportional to wavelength over aperture for a given resolution. So if I want to maintain a scientifically useful resolution of a few kilometers, and I go from L band at 1500 megahertz down to 500 megahertz, that is 3 times the longer wavelength. I'm going to increase my aperture by 3 times, and that starts getting into very expensive missions, very complex engineering to have these deployable radars. The other thing is when you get below those frequencies, there's a lot of competition for spectrum. So I referenced the ESA biomass mission, which I believe is going to launch next year. And at least as far as my current understanding is, this region here is prohibited from operating the biomass radar, because that region is covered by some space objects tracking radars that are very close to the frequency used for the biomass radar, 435 megahertz. Okay, but let's look at what is using those frequencies. Well, first of all, that's a problem because it's RFI, radio frequency interference. So even if we certainly can't do an active system if we don't have a license, and we can't do a passive system if there's anyone else using it, because any type of communications link is just going to overwhelm any passive signal you have. Okay, so I look at this is a spectrum recorded at a radio astronomy site, and this is 225 megahertz up to about 500 megahertz. So this would be the range we're looking at. And I see this really powerful signal here and this really powerful signal here. Those are geostationary communication satellites. They're licensed for, those bands are used for government communications by the US, some European countries. I believe Russia also operates satellites in those frequencies as well. Okay, so what if we could use those existing signals in a partially passive way, in that we're not transmitting, we're just receiving what's already there. But it's also active in that we're making use of a very powerful signal that's way above the noise floor. So the basic idea of signals of opportunity, I've had this animation for several years now, but we have, can't really see it here, but use some communication satellite here, and it's illuminating surface of the Earth, for end users here. There is a small backscatter. So if this was a radar, in most conventional radars, this is what you'll be measuring, the small backscatter. But since we're still always close to specular, even at high frequencies, there's a very strong forward scatter. So if we receive both this direct line of sight from the transmitter and this forward scattered signal, the relationship between those two tells us something about what's going on the surface. It might also tell something of the medium it's propagating through, but that's not part of what I'm looking at right now. Okay, so the basic idea of signals opportunity is to look at this direct signal as a reference. We don't need to know what's transmitted. We're treating it as a noise source. It kind of built upon some ideas of VLBI, and just deal with the noise source. So these are, we don't need to know anything about the signal structure except, what band it's in. And then we have the reflected signal here. Usually in signals opportunity, we've used 2 antennas and cross-correlated them. Now, when we're looking at these very low frequencies, we don't want to have steerable antennas with a narrow gain to separate the direct and the reflected. That will be, huge antennas, infeasible. But they interfere in space as well. And so if we just sample the interference pattern in space and look at autocorrelation, we can get the same information out. Okay, so there's existing signals opportunities that I know about from satellites. These are pretty well known at 137 megahertz. This is Orbcomm. It's a low Earth orbit commercial communication system. It's been operating for like 20 years. And these are the 2 government geostationary transmitters. And L-band, this is GPS L1, which we can use for, GNSSR has been well studied. Okay, so a single frequency is going to penetrate into the ground. It's going to depend upon the soil moisture profile throughout this penetration path. It's going to depend on vegetation. So a single reflectivity at a single frequency it can't really be inverted. So we looked at having multiple frequencies and doing some inversion of a forward scatter model. We used the SCOBY model. I'm not even sure if it's listed here. That was recently published. It's a specular scattering over multiple layers. And we did a sensitivity analysis where we generated some synthetic data where we took a set of USDA soil moisture sites where they have profiles recorded. So it's actual data we put into this model. I believe we used 5 years of data, generated some synthetic reflectivities at different polarizations, and then we applied our inversion here. So we looked at different combinations of frequencies. We have a vegetation model that we tuned, and we got roughness data from SMAP and scaled it to the corresponding wavelength, okay? So this shows our results. Now, one interesting thing is since we're using signals of opportunity, we don't really control the angle of incidence on the ground, and we also don't control, if they're in different satellites, we don't control the temporal spacing between the measurements. So we took a somewhat crude approach in that we put a time window on observation that we can combine into a single retrieval. And I'm not showing here, but we looked at a sensitivity to that time window because the measurements might not be simultaneous. And we could get up to 12 hours between the GEO and the LEO simultaneously reflecting on the same point and still got good retrievals. Now looking forward, of course, data assimilation, we can account for that time in the dynamic model. Okay, basically we looked at these different combinations of different frequencies and soil moisture at different depths. Also combinations of just a single polarization and H and V polarization and 2 different orbits for the receiver. And again, the orbits of the transmitters were we didn't simulate this for 5 years. We looked at a simulation of the geometry and then had basically a probabilistic description of the likelihood of getting different measurements at different incidence angles. And as you would expect, as we look at combinations of more and more frequencies, our error goes down. Okay, so the key is really to have at least one surface measurement and at least one depth measurement, right? So we could look at how complex we want to design our system, how many different measurements we want to receive, and what gives the retrieval accuracy. Okay, so I began technology development. We wrote this original proposal in 2013. We got funding for this aircraft demonstrator, which was built with Goddard Space Flight Center. These are the antennas. We use a kind of a basic null steering of these 2 antennas. And the aircraft flies east-west. The transmitter's at GEO, so we're seeing 1 point along our track. We verify, we get specular reflection of these high water bodies. We do have ground truth because of the DEX technology development that got involved in. We kind of put the detailed processing of this data on hold, but I have a new student who's funded under a fellowship who's going to go back and really try to do good retrievals with this because we also have S-band, which I haven't said anything about yet. So we have this data. We did see 2 examples of possible RFI at this frequency, possibly from air traffic control because it was near to a military airport. Okay, again, this is not chronological. We had an opportunity a year and a half ago to actually do an in-space demonstration because I had theory about this autocorrelation retrieval. I had a lot of assumptions in it. I was getting a little nervous about what we want to base a mission design on this. So we had this opportunity to test this with a communication satellite that's operated by Spire. It's reaching the end of its life, so the customer, replaced the satellite. It was just waiting to deorbit, and it had a software-defined radio. So we were able to reprogram it to record a segment at 365 megahertz. We recorded a minute of data. We only were able to download 9 seconds until it re-entered. But with 9 seconds of data, I think it is really clear. We see a specular reflection. On the left-hand side, this is the autocorrelation at 0 delay. This is the autocorrelation at the specular point delay. Okay, so this is the direct signal. You might think of that. It's the interference between the direct and reflected, and this is the reflected signal. Okay, and so as we see, it looks like it's noisy, but we get a specular reflection, and then there's one part where it looks like the SNR really increases for just for like a second. This is every millisecond. Each one of these frames is there. See, it kind of like increases, and then there's also an example of RFI. They're kind of there. We see a little bit. There's a really bad example, we think, shortly. Which is, all this goes blank. We believe it's just saturated at the front end. Okay, so we processed this data and plotted it over a map. We didn't have a good orbit because this satellite was at the end of its life. It was experienced orbit debris. So we adjusted to get the peak reflectivity land over this frozen lake. We looked at, we don't have a calibrated antenna, so we looked at ranges of G over T. I can formulate the whole equation and as a communications link budget in terms of G over T, see this peak. And then we also tracked the reflection point, and you have a bias, but again, there's a lot of stuff unknown. And we have a few tens of meters of tracking error, which all these things indicate, yes, we are seeing a specular reflection from this frozen farmland and frozen lake in the northern Midwest of the United States. I think Minnesota was where this lake was located. Okay, so then we proposed Snoopy, again, not chronological. Snoopy was well developed when we got that data. The basic idea with Snoopy was to do a technology validation of this P-band signals of opportunity measurement. And the goal, since it's a technology demonstration, we identified the forward model and the coherence as something we wanted to validate with ground truth. Quantify how bad RFI really is from space using small antennas, because we're using this autocorrelation. Our resolution is not set by the beam width of the antenna. So I think in altimetry, this would be called like a bandwidth limited resolution or a pulse limited resolution. Okay, and then of course, there's a lot of operational aspects of this instrument and the technology that just needs to be space qualified so we can go to a science mission later. Okay, so this is Snoopy. 2 frequencies, a single antenna on each. These are phased in a circular polarization. It's a standard 2x3 CubeSat. The front end of the instrument, the digital front end, did I say digital front end? The low noise front end, this part was built at Goddard. The digital back end was built at Goddard, built at JPL based upon their GNSS technology. Okay, and this is showing it being integrated and tested. There were some delays. It was originally delivered about March of this year, and then now we've been delayed, and we're going to deliver it in about 2 weeks, I think, for a launch early next year. We have very limited data volume on this because it's a experimental mission. We would like to get a well-defined samples of the delayed Doppler map out because, again, there's a lot of unknowns. So we did some simulations to look at how much data we can get out of this over a 9-month mission lifetime, and we have 3 measurement campaigns that we're planning. What I think the most important one is matchups with the SMAP CalVal sites in the continental U.S. And we're trying to keep our measurements to continental U.S. because we also have at Purdue, which is there, we have a system for monitoring the direct signal, and we can look at any power fluctuations or changes in the structure of that signal. So we think we get about a little over 50 matchups with SMAP CalVal sites. Many of them are dual matchups. Because of the geometry, they tend to have very similar ground tracks because the source is at geostationary. I didn't say anything about snow. Snow is kind of a secondary mission. We're looking at some long data arcs over snow, basically to look at the interference pattern to see how long it remains coherent in mountainous areas. And then any excess data, we could do about 1 data collection per day. Any excess data we're going to reserve for these transects of the CONUS region, again, mainly focusing on this middle part, both because that's where our calibration site is, but also the source has spot beams, so we can only really compare measurements within a given spot beam, and there's 1 big spot beam over the main part of the U.S. Okay, this is operations being run at Purdue. I guess the only key things I want to bring out about this is that some auxiliary data we need to know. We need to predict the source location.
You have 4 minutes.
Okay, I think I can be done in 4 minutes. We need to predict the source location, and since these are non-cooperative, we don't control them. We don't know anything about them. We can do that based on public 2-line elements. We believe our accuracy is good enough for those. We need our data, our orbit, which we're going to get from GPS, and then we're going to command the data collection over these sites. This is our, we had the acronym WIDE-ERP. I can explain what that means. I actually don't remember exactly what it means, but this is our monitor system. These are high gain antennas looking at the source. We're going to look at power fluctuations. There's actually the calibrated front end on this, look at power fluctuations and the spectrum of the source. Okay, we have a simulator. It was most of another student's PhD thesis, Benjamin Nold. He's now at Goddard. This is a very basic model for the autocorrelation I developed. The full model with the retrievals is hopefully going to come out in the TGARS paper soon. And I mean, this is really simple, basically specular reflection. And that's the dashed line. These are simulations for actual orbits with actual on-ground measurements. and to look at the retrieval simulation. And then for reflectivity, this is our simulation of retrieval. This is a single measurement, a single 2 millisecond integration. So of course, as we average, we can reduce that error. Okay, so other technology developments that we need. Antennas are very important. That's the one thing we're not demonstrating with Snoopy. As you can see, the antenna pattern is really weird. The gyro's also got a very weird antenna pattern. So another technology development I recently ended. We're still doing some testing of it, but I was funded to develop this antenna from, and I subcontracted this company MMA, who did the actual RF and mechanical design. It's deployable. It all folds up into 2U spacecraft. We did some testing with actual signals at Purdue, and now the algorithm development using that same tower. We have this all ready to go. It's installed in the field right now, but it's pretty much the end of the agricultural growing season, so there's nothing there. So really just doing some engineering tests before we take it all down, and then next year hopefully get a good 1 season of data. We have 4 frequencies we're looking at. These are all commercial antennas because these are all communications satellites. We just need to get the antennas, the polarization reversed. The direction, we're looking at geostationaries in that direction. We have a calibrated front end that uses, I believe, 4 points in noise loads to do the gain calibration. Okay, we're doing 2 measurements. We're doing some at this agricultural field, which I've used many times before. If we get funding from one of 2 proposals, we're also going to do some experiments in this very well curated forest in the forestry department. Okay, so conclusions and outlook. I think SALT provides a new opportunity for microwave sensing in bands that we've not been able to use before. I think it's very important because it enables new measurements we've not been able to make before. Snoopy is going to demonstrate the basic technology. It's a tech demo. We have a multi-frequency dual polarization antenna prototype for possible future science mission proposals. And we're conducting algorithm development. So what are my recommendations? A lot of stuff is different in the forward scatter with signals of opportunity. So there's a lot of potential for algorithm development. I think we've just begun to look at the algorithm developments in forward scatter. Algorithm development, of course, needs field experiments to validate it. And then also we need to find, clarify what the science question we want to answer if we go forward with a mission based on this technology. I mean, root zone soil moisture is an important measurement, but we need to look at different science questions. And that's basically what my recommendations are.
Very good. Thank you very much. We don't have time for questions, sorry. Our next speaker is Wolfgang Wagner from the Technical University of Vienna. So let's welcome him.
Can you help? So my talk is motivated by the fact that we see at the moment many papers of using artificial intelligence for soil moisture retrievals. I'm trying myself to make some sense out of it also as a reviewer, looking at the paper, what can we really learn from those papers? So this is an attempt and relating it to the soil moisture research we have been doing for many years. A co-author is Bernhard Ramel, who has been working in this field. So we have had some very interesting discussion that went into this talk. So there are obviously many advantages of using these new machine learning artificial intelligence models, and obviously is a big hype around ChatGPT, and we all know that it can do fantastic things. And if you put into things like, if you ask ChatGPT to praise the use of artificial intelligence for the analysis of Earth observation data, you find many good, really strong points. But you also find things where ChatGPT hallucinates, basically tells you completely wrong, stupid stuff. Like, for example, if it tells us that artificial intelligence is great for us researchers because then we can focus on interpreting results and making informed decision. I think this is exactly the opposite with machine learning, because it's a black box and we can't really make informed decision, nor can we analyze it if you don't understand why it works the way it works. Obviously, I've also been involved, like one of my PhD students has also tested the use of AI models, in this case, a gradient boosted regression T algorithm.
using Sentinel-1 data, and he has used a very large in situ database extracted from the International Soil Moisture Network, and also using data for many years. So he basically used the Google Earth engine, extracting backscatter time series, and then calibrate, basically putting all the data from Sentinel-1 and from the in situ database to train that model. And you see there on the right-hand side the result. So overall, like, you get very good results, and you get into root mean square errors that are really acceptable, and for example, that are within the mission requirements for small sense map and most of the other satellites that we are having. So obviously there's a case that you would say, well, I want to use an artificial intelligence models and ingest many different data sources into the model. If it's now microwave data, if it's optical data, if it's auxiliary data, terrain data, soil data, and I use in situ soil moisture data for training the model. And then you get soil moisture data out. And this is done now by many papers and that are published. For example, here's a paper that was published in Scientific Reports of Nature, so quite high-profile article. Basically, they used a neural network and put things in from Sentinel-1, the VH and the VV channel. Interestingly, they are not just used the channels as themselves, they also used ratios into it, and they also used information like latitude and longitude to derive soil moisture, which you can ask, well, why do you put two variables in that are not related to soil moisture? In terms of the in situ database they used, actually they had two field campaigns collecting overall 224 in situ measurements with these kind of in situ measurements. So it's a very simple sensor. You plug it in and you plug it out. You make a soil moisture reading, and these measurements may be precise, but they're not typically not very representative of the pixel that you're measuring. There's a huge field scale gap between that little measurements and the satellite measurement, even if it's only like 10 or 20 meters. And then you say, well, you use those 224 values for calibrating at least something like 3 million satellite pixels. Anyhow, it's, they've did it, and then they get maps out of it that look something like this. So they're beautiful looking maps. But if you ask me what's my confidence in this kind of maps, well, I would say it approaches 0. So what can go wrong? I tried to illustrate it in this graphics. So, well, we can start with the first point. Many papers use too many input features, including input features that are not of relevance for the process itself. And some of the input features are often highly correlated, which makes then also problems when you're in the calibration of the artificial intelligence model. In the case of soil moisture, we also have a problem that, we also, in many other cases, we don't have matching in situ on model data. Yeah, that's not really doing the same measurements, they're not representing the same process. So that can be very dangerous. Then we have a huge suite now of very good and strong models, but many of those models are actually often too strong, too powerful. So we have overfitted and oversized artificial intelligence models. And then you get super duper results out of it. And you can ask the people, well, how can you interpret this very nice looking map? And then you said, well, actually, I don't know how I can give you an interpretation. I don't know how it works. I don't know where it works. I don't know when it works, but it looks good. So let me go into each of those points that may be critical, particularly for soil moisture. For example, in soil moisture, we have this, I already said, this mismatch of in situ and satellite soil moisture data for many reasons. For example, there's a scale mismatch. So in situ measurements, most techniques just represent a very small volume of soil, so maybe at best a cubic decimeter, while the satellites at least represent a hectare to several hundreds of square kilometers even. Then we have a depth mismatch. With in situ data, you're always a little bit below the soil profile, like the soil top, so at least at 5 centimeter. Many measurements also at 10 centimeter, and some then also at 20 centimeter. So that really doesn't translate from the thin surface layer that we measure from the satellites down to the measurements where the layer, well, not in situ data then gives you. And we also have the interesting thing is
But also, of course, in situ data are not perfect. We have now many in situ measurement techniques and all behave a little bit different. So if you look, for example, at the dynamics of the soil moisture data stored in the International Soil Moisture Network, they look different depending on the technique that you're using. So there's many different reasons why actually it's not so straightforward to use in situ data to use it for the calibration of machine learning models. That is why, for example, we at TÜV, we don't use in situ data for calibrating our models. We only use it for the independent validation together with model data and more advanced statistical approaches like triple collocation to give us a feeling where actually the errors are. Yeah, and then the question is, well, if it's true what we now already do in the soil moisture field, why should it be different if you use artificial intelligence models? So what kind of reasons would be there that it thinks it can be solved if you do it for artificial intelligence? The next point I'm a bit concerned is when you look at different data sets, they often, you get very high correlations spatially and temporally. Just for example, if you plot here, like we've been studying recently, soil properties and how it relates to the interaction of microwaves, and then you try, of course, you take different other data sets like leaf area index, you take elevation, you take also antecedent like soil moisture conditions to understand what's there. What we are seeing is all these data sets are naturally highly correlated. Obviously, if you're in a dry climate, you don't have as much vegetation that has an impact on the soil. That's clear. But on the other side, all of our communities, for example, soil people, take vegetation data to train their models for creating soil maps. So then you can ask all these models, maybe we're a bit in a cycle that we use each other's information and we kind of approach a certain representation of the land surface that is too correlated. And I think in many cases it can be also the same. Then on the overfitting problem, so using a too strong artificial intelligence model. So if you look at the overfitting problem, it's really funny to see like how different scientific community see what constitutes a complex model. Yeah, if you look into the AI and machine learning community, obviously they use many parameters. Like if you look at ChatGPT-3, so the one that has been released last December, it has 175 billion parameters. So that's amounts that you're having. At TÜV, we also have very strong informatics people that do big data analysis and also machine learning. And they, for example, had a press release about one of the new paper and said very proudly, oh, we only use 75,000 trainable parameters, saying this is really a huge advance compared to other state-of-the-art models. And this kind of view can, of course, then be confronted with how mathematicians and physicists think about the problem. Like, for example, this famous statement from the genius Hungarian mathematician von Neumann. He said, well, with 4 parameters, I can fit you an elephant, and with 5, I can make him wiggle his trunk. Maybe it's a bit overexploited, like to emphasize too much. But the point is really, if we get into like 5, 10 parameters, you can already do a lot. So, and this kind of overfitting problem, I think, is now also in our work, and it's really very difficult to get out. For example, this is a work from a very good student from Susan Steele-Dunn, Xu San, who has been working on using land surface model parameters, soil moisture, vegetation, to explain what we're seeing with the advanced scattorometer, the ASCAT, and both explaining the backscatter intensity and the variability of backscatter over the incidence angle range. And it's basically created for each pixel a deep neural network for explaining from the land surface model parameters up to the satellite observed data, and there's a very, very good match. What he then did, he used then like basically a method for checking the sensitivity of the neural network. So he calculated normalized sensitivity coefficients to see what the response is of the satellite data to the input data, and explaining this for different type of land surfaces. So if you look, for example, at grassland, So we see that grasslands, if soil moisture goes up, backscatter goes up. We see if leaf area index goes up, there's also a certain tendency, but not as strong. But what's very interesting in those plots is the strongest response is this one here. We cannot explain from the data. This is most likely a spurious effect that comes from agricultural practices that are not being described in our data set. So the neural network most strongly responds to something that's not, we cannot describe. So the question is, how can we prevent now AI models from running wild? And I think being a physicist, obviously, my first reaction would be, well, let's try some physically based models where that had a couple of variables that we can look into and really have a good understanding what we are doing. And then you can use artificial intelligence techniques, for example, for exploring the data first, trying to understand the data space, how, what kind of things my model needs to do. It can help me for estimating model parameters. It can help me approximating some unknown processes. I'm not saying that every physical model can do everything. So there's always some good things where we could say, well, we try to approximate that unknown process. And we're using, there are 3 different models like change detection, zero, like rate of transfer models with zero order solution and with the first order solution. Just for example, our first order rate of transfer model developed by Raphael Quast, where we basically model the phase function for the vegetation and for the surface, also being able to describe very complex surface vegetation interaction effects. This model has recently been used for producing a new data set that has been produced within the ESA digital twin activity on the hydrology. So where we did a 1 kilometer soil moisture product for the whole Mediterranean, giving us very good results. But I also have to say the RT1 model is so powerful, so actually we had to strip it down to the very simple, most basic parameterization to get robust parameters out of it. So that, yeah, it has been a model parameterization, even with a physical model, is extremely complex. Yeah, for this kind of optimization, we use a trust region reflective Levenberg-Marquardt algorithm. As it has been mentioned sometimes on this conference, and also so in the previous talk, obviously with microwaves we see into the ground, and some of our problems in the soil moisture retrievals is that we see signals from below surface. Just saying, within this data set, we have identified those areas where we see subsurface scattering signals. We have masked those areas. The good thing is they are very localized. That has led to much better results, for example, for the whole of Italy. In other regions, like in Spain, it's much bigger problem, and even there, this approach works nicely. So what's our current take on the current situation? So certainly artificial intelligence techniques have become extremely powerful, and this can be exploited for the good and for the bad. And really, you need to look into each study, into each methodological setup, on which side you are, or if you're in the middle. So if you look where in so much applications AI models have become particularly popular is when processes are not understood. Then the first reaction is, I use artificial intelligence. The second reaction is when you talk with people, well, when things need to go quickly. Like a statement from a good colleague who said, well, we use artificial intelligence because I can't wait for the physical models to be developed over time. I need quicker results. The last point is very important. Well, if you do data assimilation, so basically if you take your satellite data and try to put it into a complex modeling system like a land surface scheme or atmospheric modeling system, you anyhow want to transform the data space into the model space, so doing real proper data assimilation, then also data assimilation or artificial, like these models are a good choice. Yeah, but then we get high resolution soil moisture estimates. But now we're in an unfortunate situation that we lack the data and tools to validate those data. So it's not simply that you look at the data and you say, well, this is good or this is bad. We just don't know. That's really a problem.
So my question that I'm posing myself is, well, the use of artificial intelligence models can be a quite quick win, but will be regretted later. So in terms of outlook and recommendations, so we're gonna, like in terms of the outlook, we certainly will see more and more use of artificial intelligence in soil moisture studies. I'm sure we're gonna review many of those papers. And we're also seeing already now that we get more and more high resolution soil moisture data sets that look pleasing to the eye. But there's, like, I guess some of them do not generally depict soil moisture, but more indirect indicators like vegetation or topography. And I would say that as long as we don't question the use of artificial intelligence more critically, it will be difficult to expose scientific errors. So the recommendation is that we should focus, we should shift the focus from producing data using AI models to understanding to actually what is happening. So we need to develop models and workflows that contain somehow checkpoints. Yeah, checkpoints could be, if you use a physical model, the model parameterization. So you look at each individual parameter. Does it make sense? Do the spatial patterns make sense? Are they within the expected bounds of the physical defined unit? But of course, also, you don't necessarily need to do a physical model. You could also use sensitivity tests to depict dependencies, as, for example, was being done by Chushan. But I'm sure there's many other possibilities of how you can try to make sense of what's in an AI model. Then also, we need methods for estimating the effective spatial resolution information content of soil moisture data, because if you have many input data sets, you don't really know where the information is coming from and what the effective resolution is. The point is, sampling is not the same as resolution. So what's really the information content? And last but not least, of course, we need now in this age where we have better satellite data, we need many more and better in situ data. Thank you very much.
Very well done, and thanks for finishing on time. As a reward, you can have many questions.
I can have many questions. Please.
Hi, Wolfgang. I really like the presentation. It was a little bit negative, and I think that a lot of the criticism I don't necessarily agree with personally, but if I look at the recommendations, it really go in the direction of let's just not do machine learning and keep on going into physical understanding and so on, more in situ measurements. So it's kind of like, okay, we're just not going to ingest this. So if we flip it around a bit more positively, what is that you actually see room for with machine learning?
Yeah, maybe it came over a bit too negatively, but I think we use it ourselves now very heavily to, again, for the points that we have mentioning. So data exploration, really understanding what's in the data. So we use it for the the estimation of model parameters. Sometimes you can maybe estimate model parameters in certain locations only. Then if, for example, you can use it for extrapolating in different fields. What I'm saying is, what I'm very critical is that you build a database and then you use machine learning and then you get a result out that makes sense within the existing context, but you have no way of checking and controlling what's inside. That's what I'm critical of. But otherwise, I see many different purposes. The point is, I'm seeing so many papers now that are really, I don't know what to make out of it. So it's a trend and it has been promoted by space agencies like ESA, saying, well, use artificial intelligence because it will give you a boost forward. So I think at the moment, maybe the tone was too negative because I think it has been hyped, too much hyped. And we need to go back one step. Certainly we're gonna see and they use it.
Thank you. Last one.
Very nice presentation. Just one question. So deep learning has been used in different disciplines, not just hydrology, and some of them are really critical. So soon we will see deep learning in medicine, some fields that it's much more critical than hydrology or water. I think for many other fields, they have developed their own sort of criteria to check the models, because we are heavily reliant on the models that have been developed by computer scientists. So maybe they don't have this idea about the physics behind. What's your comment if we should be active more in our society and develop our own criteria for checking these models, and then inform people, and then you would have better reviews of the papers, and we have better things to check if those criteria are not checked?
Well, I certainly think that it depends on the application, what needs to be checked, and where you have to be careful. But again, I think it can be different from field to field where it makes sense. For example, if people use it now to increase the efficiency of the weather forecasting, so if you have a big, powerful network that is trained on weather forecasts, and if it's just used for the purpose of making the next forecast more efficient and more timely, that's good. But the next step would be too far to say I can replace my complex weather model with a complete machine learning approach, because that's nonsense. You need the complex modeling system to actually control the system and keep it. So we need to distinguish between what's good and what's not good. The same as if we use ChatGPT, we need to learn what's nonsense and what can be used. So we are always responsible ourselves. What kind of information we extract, what do we trust? And that's going to be very difficult.
So in that direction, we get a lot of questions, and we always know these metrics to check our models and stuff, but we normally don't ask questions about, we all just know the cross-validations, these terms that they already know is known, but I think we should develop more. Thank you.
Thank you.
Thank you.
There would be one more question. If
I
not, there's
don't think we have.
Yeah, you move on to your talk. So I hope good introduction to your talk.
Yeah. Actually, I'm a computer scientist. I work in machine learning. I take it very personal, you know. It's a big attack there, you know. Yeah.
Speaking of Mike, we will record it. Just a small message that at 1:30 at the end of the session, you're all required to go to the staircase. We'll take a group picture. Thank you.
Okay, very good. Thank you. So, good afternoon. My name is Francisco Peña. I work jointly at Stockholm University and KTH in Sweden. And I'm going to present you a deep learning model that helps us to detect water from SAR imagery. I'm pretty confident, or I was pretty confident about my model until 20 minutes ago, but let's see. So, you know, the main goal that why we want to do research on detecting water using radar imagery, it's because we want to preserve wetlands. Wetlands are extremely important ecosystems, as you know, they help us, contain floods, purify water. They're home to a wide variety of flora and fauna, but they're very particular because like in some cases, most of the water in the wetlands is hidden under the vegetation. So, using optical sensors, we cannot really know what's below the vegetation. And also they change, the extension changes over time, depending on the season, during the spring, they have a big extent. During the summer, it shrinks, and then during the autumn, it's kind of enlarging again. So we want to be able to know how they're changing over time. And for that, we're using remote sensing data. So, when we started this project, we say, okay, we have a few options. The first option is an optical-based method, but, it only works when there's daylight. As I told you before, it cannot penetrate vegetation. It also cannot penetrate clouds. And, in regions, especially in the north of Sweden, there's regions where, there's almost a cloud there like all year round. So we cannot really see how the wetlands are changing. So we say, okay, maybe a radar-based method is the best. So We can use like a threshold-based method in which we say, okay, values that are higher than this intensity, we classify them as water, and the lower than this intensity as not water. But they're very sensitive to noise, and they do not consider surrounding pixels. So then we say, okay, maybe if we use machine learning on the radar imagery, we can do a better job. It turns out that these type of models are more accurate, but they require large amount of manually labeled data. This is a really nice graph, a bit controversial at the moment, but it shows us like with the traditional machine learning models, there's a point at which even if we give it more and more data, the performance is not going to improve. However, with neural networks, the more data that you give it, the better it's going to perform. There's a complication with this, and where's the, is it? Yeah. So you see amount of labeled data. That means that if I want this performance, I have to train my model with this amount of training data. That's a lot of data. So how many of you here, just raise hands, how many of you here are using machine learning? Wow, okay, big percentage. How many of you have struggled to get labeled data or clean or clean the data to train the models? Well, like all of you, okay. So it's a big problem, right? And it's such a big problem that I just made one slide. I'm going to spend the whole minute so that we appreciate this. The biggest entry barrier to a deep learning project is the lack of annotated data. And since it's so important, I'll say it again. The biggest entry barrier to a deep learning project is the lack of annotated data. So, we see these wonderful models with wonderful performance, but they can only work in the sites where they have collected the data. So, we have a lot of wetlands in Sweden, but I cannot pretend that a model that has been trained on Scandinavian wetlands is going to work well on sub-Saharan wetlands. So then the people, like let's say the researchers in the sub-Saharan Africa cannot really use our model unless they collect all the amount of data that we have collected. So we wanted to tackle that problem. Then, just to illustrate how we're doing things, we take a look at here. There's an optical image on this side. We have a wetland which has a lot of vegetated water, and on this side we have a lake which has no vegetated water at all. Okay. With the radar, we can actually see that there's much more water than what it looks in the optical. However, I want you to focus on this part. The size and shape are exactly the same, okay? So we exploited this property because actually detecting water from optical imagery, it's, we could say, a quite easy task if we use a water index model like NDWI. I guess most of you are familiar with NDWI, but I will just explain it very briefly. It's composed of green and near-infrared light, and there's a very cool property of near-infrared light, is that when it's touching the water, it gets absorbed by the water. But when it's touching soil or vegetation, it gets highly reflected. So it's very easy to distinguish water from not water using near-infrared light and green light. Basically, that's it, okay? So we developed our models, which is called Deep Aqua, in which we take bodies of water that have no vegetated water, and we apply NDWI, and then with this, we create a water mask, okay? Then we take a deep learning model, in this case is a convolutional neural network, and we train it on radar imagery from the exact same region, okay? And then we make a prediction. Then we compare the prediction of the neural network against the water mask that we produce using NDWI, and depending on the amount of error that we have, we update the weights of the neural network. We repeat this over and over and over and over again until these two predictions start to become very close. So, here are some results. We can see that, compared to other state-of-the-art models, there's some variations of our model, and they all mostly outperform the other state-of-the-art models. And just to illustrate a bit how it performs, here we have some very noisy images of different wetlands across Sweden, and we can see that there's some models that struggle with the noise, but ours is quite resilient. And here we have the ground truth. We can, using our model, then we have started seeing the seasonal patterns of different wetlands across Sweden, and we can see, it makes sense. We have some outliers. I didn't want to remove this. It's part of the real world predictions. And, we can use it then to see which wetlands are degrading faster over time. Also, in our lab, with one of my colleagues, we're working on mapping 68 Ramsar conversion wetlands across Sweden. And I wanted to show you this image in which, we can see how good the delineation of the water is. But, I'm also happy to show you that, it doesn't work perfectly. So, for instance, here we have snow. Here we have no water in the radar imagery, but our model is predicting that there's water because it gets confused by the snow. So right now, we only use our model, let's say, with images without snow. Next steps, things to improve. So right now, we're working on another model based on the fact that the really valuable data to learn from is the edge cases. So there are many cases in which the water is not really distinguishable from soil. So if our model is able to get over those really difficult cases, then it's going to really improve the accuracy. So, using NDWI and a convolutional neural network, we can actually create a water mask that is continuous. And here the yellow parts are, let's say, the most difficult cases. So if our model is able to imitate those difficult cases and get over that, then it's gonna have better accuracy. Just to, to finish, now that we're talking about GPT and all of these kind of things and, how they're using in medical images, this was a tweet from 2 days ago from Greg Brockman from OpenAI, and he was saying the new GPT-4 model is able to have the same performance of writing reports based on radiology scans. So, it makes us wonder, what's going to come next. Conclusions, our model requires no manually labeled data. It outperforms the state-of-the-art models like Dynamic World. I'm very proud to say that it was trained on an M1 MacBook Pro, my personal computer. So, anyone can load our pre-trained models. Anyone can train Deep Aqua for their own regions. Here's the GitHub repo where we have the model. And, just outlook and recommendations. Look, if we want to have a big impact, we should aim to create methods that others can easily use. It makes no sense that, my method works great, but then you have to collect 20 years of data to be able to train your own model. So we want to bring down the adoption barriers. And regarding recommendations, our focus and recommendation is to create models that do not require manually labeled annotation. Wolfgang was talking about, collecting 224 samples out of a 3 million or, 50 million site. So, if we only relied on that data, it's going to be impossible. We cannot collect that much.
and also bring together different types of data. Right now we're only using radar, but it would be interesting to join in the same model, multispectral SAR, INSAR, and LiDAR. That's it. Thank you very much.
Thank you, Francisco, also for the catching up so much in time. So we have time for questions. Like, I have a question. We also do water body mapping, and don't be concerned. We also there I see machine learning models can do a lot. But one question is, have you tried your model on the for example in the same area where there was no water body? Because we find it's easy to do like a classification of an image in the area where you have water bodies, but then if you move it into another area where there's no flood or no water body, it's actually they fail quite quickly. Have you tested?
Yes, actually we take entire regions where there's absolutely no water at all. So we actually have a bit of a class imbalance problem where most of the images contain no water, and there's only a few that, well, not only a few, but a smaller percentage contain water. So yeah.
Are there more comments, questions? Good, thank you very much.
Pleasure.
So we have now. Yeah, so we have now 10 minutes, and then the picture is taken, as far as understood now. Well, and we have thought about some seed questions for the session, but now I have also had some discussions, for example, with Jerome, said, well, where can we bring up the bigger questions? And now you know that I'm somebody who likes controversy and maybe the bigger questions. So I was thinking, these things are really very close that concern me at the moment when I'm observing the situation of Earth observation in Europe. I'm not sure if you know, but the plans are that functioning satellites are planned to be parked in an orbit because of the ground segment costs. So, for example, if Sentinel-3C will be launched and Sentinel-3A and Sentinel-3B are still basically working, still Sentinel-3A would be parked in another orbit. For the reason that the ground segment is not big enough or not powerful enough to, and too costly. And as a taxpayer, I'm well, now we build a satellite that's really great, it was expensive, it's fully operationally, and then we put it out of order and not using it. So that really, I think, so far, when we looked at all of history of European Space Agency, of all the satellites, if you look to the US side, and I can't say so much about the India and China side, but we've always kept the satellites working until they failed for whatever reason. And now the near future may bring that we put them out of operations. And particularly for us hydrology community, I think that's a big shame. We depend on high temporal revisit time, and I would like to see 3 Sentinel-3 satellites in orbit. The same I would like to see 3 Sentinel-1 satellites in orbit. At the moment, I'm fearful, that we keep on the one going until the Sentinel-1C is launched. And if we as a community would like to have this as a recommendation, they could go into this workshop report. So maybe, who thinks it's a good idea to keep on satellites that are functioning, to keep them operated? Hands raised. Okay, 50-50, so we need to take the other example. Who thinks it's a good idea to shut them down? Okay, no hand is raised. Could this be a recommendation from this workshop? Please don't shut down the satellites. Yeah. Okay, very good, thank you. And it was an easy one. Yeah?
Obviously, no one would vote for or would be in favor of shutting down a satellite that is perfectly functioning. But I would like to understand what is the other story. So what do we miss, or what do we have to pay on top of what was already expected to keep them all functioning? So that there's always a gain, and we gain in one hand and lose in another. And it seems that the whole story is not being told.
Well, obviously, like if you keep on operating the costs of a satellite, it adds additional costs. And for example, one understanding is that they don't have enough ground receiving capabilities, so they would have to see more ground reception station, more telecommunication systems. So it has an additional cost element to it. But then if I compare it to all the other costs that have brought us up to the point, and if I say, well, I've now spent, I don't know, several hundreds of millions of euros, and now I don't spend the 1 million euro to keep it going, I think that's a waste.
So on top of what we've been discussing, it seems to me that there's an issue with planning, with a long-term planning.
Well,
if we come to this situation, and in that sense, I would also add something on lessons learned. So why are we even asking ourselves this question at this point?
Because that's new. Because so far, ESA and EUMETSAT have always maintained being able to run the missions. They did somehow find money. It was always planned to be shut down. But in the end, they always managed, okay, there's a great satellite. The scientific community always said it's great. And they found money to keep it going. Now we seemingly are in a difficult situation that we need this step. Yeah.
If you're gonna, can you say in the microphone, because no one can hear you. If you have something, please. Can you say in the microphone?
A review process carried out by the agency. After a certain point, they review whether or not the satellite is useful and what is the cost, and balancing the benefits. And I mean, I have the experience from NASA when they have missions, GPM mission, CloudSat mission. When they do a review, they say, okay, now, is the satellite functioning? How much is the cost? How much is the benefit? And then they
I think they know. I know they know quite well. It's a political decision. It's a prioritization of what you need to do.
There's a certain amount of budget, and then there's budget priorities, and then they get listed in budget priorities. But for us to come to the conclusion as a community that we want more data, or we want to keep things functioning, this is almost obvious, right? Of course, we would. But obviously there's some trade-off in a budgetary prioritization that we are not aware of. So it's difficult to say what is being sacrificed in order to enable that first point. It's tough. It's tough to say. We don't. I mean, if we had a clear picture of what the trade-off for that is, then maybe we could make a better comment on how to do that stuff. But
well, at the moment we are in a difficult situation. We have the launcher crisis in Europe, as you know. So that puts additional burden on developing rockets. So that's sucking away money. So some of the satellites are already delayed. So that also costs additional money. So we come in from a launcher crisis into a crisis of the future satellites launches to a crisis of operating systems. So overall, it's a much bigger problem. But again, it's more like space agencies come to us scientists and ask, do you want to have this new satellite? And our response is, yes, we would like to have a great new satellite. At the other side, we don't seem to exploit what we have to the full extent. And I think it's important to raise the flag that we should better exploit what we have, and we should keep it running, because that's where the operations are.
This is a beautiful discussion, and it's really important to raise this point and have it in the report, I think, because it is really, really important. I mean, it's the same thing everywhere where there's a demand for continuity in the science communities and operational communities. But I think the space agencies always also have an incentive to do technological development. It's part of the mandate of what they do. So there's always pressure for them to come up with a new concept, a new idea, because it employs engineers and it makes, it drives technology forward. This is a great discussion point to include, though. So thank you.
Thank you.
Yeah.
Well, the second point is actually very much related to it, because I'm also worried that more money goes again like into the hardware and not being exploited, or not, we don't have enough money actually for doing the data exploitation. You know, that we even, like ESA has satellite programs where they don't really have any significant budget for the scientific exploitation, but it's more building a satellite, launching it. Maybe Matti, I'm looking now to you, the Scout program. It's you know, an idea to launch a small satellite system very quickly, develop it, but then there's hardly any funding for operations and data exploitation. I think it's a wrong approach. So I think we scientific community would say, well, we expect the data to be beautiful, they come out of hydrogen ESS, let's exploit them. But in order for us to exploit them, funding would have to be there. So it's a programmatic issues and of priorities. Maybe Martin, you could support the point saying, well, we need money for the scientific exploitation of hydrogen ESS.
Thank you, Wolfgang. Of course, I'd say that, but I would say that it's hydrogen ESS. Well, I'll be talking about it this afternoon. It's a brand new program, Scout program, and because it's so new, I think people are trying to still work out what the shape of the Scout project is. So, yeah, there is a need to exploit the data, and we're going to encourage people to make use of it as much as possible.
Well, it's just one example. It's just one example. I'm also thinking now about the beautiful SWOT data, you know, and the US is good, and the French people are good in exploiting the data. In other countries, you know, we don't have really programs yet to start exploiting the data.
No, I think people are aware, and something will happen, but yeah, something has to happen. Yeah.
So maybe a quick, since we only have like, what is your support for the second one? Is this also like a support we can politically formulate, that we need more funding for the exploitation of the data? Is it a no-brainer, or is it a bit more contested? Who is for the no-brainer? Okay, that's already much more. Okay. And those who are against it, who say, well, that's a bit too vague, too shaky, that statement? Well, we have one comment, maybe the last one.
Just want to ask a question. What exactly do you mean by exploitation? Is it scientific exploitation? Do you mean operational exploitation in like applications that are used on a long-term basis, or what do you
There's more related to it. For example, it's always a big question. At some point in time, you need to be able to reprocess data. And for example, for the Sentinel satellites, it has never been planned a priori to have a reprocessing activity. So every time there's now a reprocessing activity, there's a huge effort for the space agency to argue why this reprocessing is needed. And I think that there should also be a no-brainer that we evolve with the science, the mission evolves, there's changes in the data format. At some point in time, you need to have reprocessing regularly, and that needs to be planned from the very beginning. But that's at the moment not the case.
Right. Thank you.
Okay, so thank you very much for your attention. So I think we should have the group picture, and thank you for feedback. Thank you.
Thank you.
Right. Hello and welcome everyone after a very wet lunch. Thank you for still making it back. I wasn't expecting to see many people back maybe. Right. So today it's my honor to welcome you with my co-chair, Claude Duguay, for the Novel Technologies and Future Missions, the Future of Water Cycle Research. We do not have the first presentation, and so we wanted to kind of talk a bit about the role of novel technologies in water cycle research. The presentations we have today will talk about several new and exciting missions, the Hydro-GNSS, building digital twins, GNSSR, which in the last couple of years has become more and more popular in water research, and also looking at CalVal of satellite altimetry missions using autonomous UAVs. And we were wondering if we could show you already the seed questions so that you have a chance to reflect while you sit through these really wonderful presentations, and so that we can have a much more charged discussion at the end. So one of the first things that we wondered from the community were barriers or what are the needs for different applications for the spatiotemporal resolution of products. We were wondering specifically which hydrological applications are still limited due to spatial and temporal gaps in Earth observation data, and what we think as a community we should do in this regard, or what exactly we think are the needs for specific applications. We were also wondering what are the barriers now with so much data, so many machine learning algorithms and so much compute capacities. What are the continual barriers we face in developing gap-filling algorithms because they are still not enough for hydro-EO products? The second topic we wanted your thoughts on was calibration and validation. Especially in cold environments, it remains one of the lesser studied areas, as my co-chair would perhaps also tell you. And we wanted to really have pick your brain a bit on how the development of CalVal standards could be promoted for every subfield of hydro Earth observation. And specifically, how could the CalVal in normally not observed places like the Global South be improved? The third topic we wanted to reflect on together was EO and model integration. And in this context, we wanted to ask you what are the barriers we still see to scale relevant model EO integration in a variety of implementations. We wanted to hear from you if you think there is a need to develop specific guidelines for uncertainty estimation, especially for EO products, and how far are we in the space. And specifically when tailoring merging approaches to applications, what are the considerations for EO product developers, let's say, to consider to allow this merging to work optimally? Finally, we wanted to talk about hybrid Earth system models, so combining all of the sources of information that we have in a complete modeling framework, and to see how far we are with that and what do we need more to go forward. We have also some more session-specific questions, which are really related to what you will see here today. So feel free to use them in your questioning of the speakers, and also for you to critically reflect on the presentations we will have here today. Specifically, the digital twins. Where are we now? Where do we want to be for an operational system for it to actually help with our climate change goals? Or climate change adaptation goals, and what are the barriers still to operationalizing such digital twin systems in reality today? Then also looking at UAVs, how can we leverage them more as environmental monitors? Can we have citizen scientists as drone operators? Can we have automated drones, something that we will hear about today? And finally, for GNSS, we wanted to discuss if we are ready to increase its use in land surface hydrology applications, specifically for model data integration, and also trying to think about how it could maybe plug the gap for some of those spatiotemporal gaps we have still in our EO hydrology products. Claude, do you want to add something?
No, that's, I think, it for the C question. So it's really for you to start thinking. We're trying to fill in the 20-minute gap here that we have at the beginning, but start to think about those. Maybe we can leave them up, maybe the more general ones. And of course, we'll try to start the presentations in about 8 minutes or so. I would ask the speakers to use maybe 17 or 18 minutes for the presentation. If you wish to get any questions. Otherwise, use 20 minutes, but please don't go above 20 minutes. I will show you, I will wave after 17 minutes. I will wave at you to asking you to wrap up. And yeah, that's about more from the operation side of things. And
right, maybe more housekeeping stuff. Please come to the mic as soon as you know you would have a question to make it go more efficiently. We look forward to an engaged session with everyone contributing. Thank you.
Pardon me? Yes, we'll start in 7 minutes now. But we can keep the questions maybe up, the seed questions up.
We should give him a few.
You have to move the cursor.
Just trying. I'm just going to close this one and we'll open.
Are you presenting? No.
No, actually, Martin, but one of my PG students will be back. Sure.
Nazar Verdika, I studied with him. He was one of my professors.
Martin.
You can use the part if you want. Center one is the Mason and then back end.
Yep, good. Okay. Okay, so we'll start our session. So the first speaker is Martin Unwin, and he will be talking about the ESA Scout Hydro-GNSS small satellite mission. Martin?
All right, thank you very much for the introduction. And I'd like to acknowledge there's quite a team of people working on this. You can see the names of the organizations underneath, and also with the ESA team and my SSTL colleagues working on the Scout mission. So a bit about what Scout is. So Scout is a new kind of mini Earth Explorer program that has been set up by the ESA Earth Observation Directorate. And the aim is to show that science can be done with small satellites. The budget is 30 million euros and 3 years from kickoff to launch. And the data will be free, full, and open, and delivered using a service-based approach. So that's the aim of the Scout mission, Scout program. And Hydro-GNSS was selected as one of the first 2 Scout missions. The project was kicked off in October 2021. And in February 2023, they managed to find, we started with a lower budget, but we managed to find the budget that supports a second Hydro-GNSS satellite. So we have 2 Hydro-GNSS satellites in the mission. The company I'm in is Surrey Satellite Technology Limited, and we're priming and leading the team of international scientists, including from Italy, Spain, Finland, UK, Austria. And there's a picture here from the calibration validation workshop that we hosted in March earlier this year. So a bit more background because I'm conscious that a number of people won't know where this has come from, people with different backgrounds. So what we're doing is we're using GNSS signals as a radar source. So global navigation satellite systems, including GPS, Galileo, and others. There's more than 100 L-band sources in orbit around the Earth at 20,000 kilometers plus. They have a wavelength of around 20 centimeters. And they're continually transmitting power. There's about 50 watts per signal that's being transmitted down by each of these satellites. The bandwidth varies. It's the one that most people use is 2 megahertz wide, but there are some wider signals which go up to 40 megahertz. And the signals are designed for navigation. They have atomic clock stability. And of course, they're used for, it was designed for the military, but it's found plenty of civil applications as well. Airborne, ship, land vehicles, and of course, mobile phones powering your Google Maps. Now, normally these GNSS reflections are referred to as multipath. They're unwanted. They can give false position. They can be quite dangerous for navigation. But in the 1990s, there was strong reflections picked up by a jet plane over the ocean that showed that it was possible to pick up these signals reflected off the ocean. Could they be used for bistatic radar sources? And there was a lot of interest because in terms of radar, you don't need a transmitter. You just need a modified GPS receiver, an antenna and a receiver. So there was a lot of background work. I won't go into the history here, but we did fly an experiment on UK DMC back in 2003. And it was a bit grabbing experiment to show that it was possible to pick up these reflections, that they contained signals. We just did a bit grab of 20 seconds, sent the data down to the ground, and then processed it with a software receiver. And then we found that reflections, we thought we might just pick them up over flat ocean surfaces, but we picked them up from all states of the ocean, whether it was rough or smooth, and we picked up reflections off ice and off land. So that kind of kicked off spaceborne GNSS reflectometry. The early concepts led to an instrument development and a key in-orbit demonstration on the UK Tech DemoSat-1 mission, where we actually processed the signals on board. And the SSTL instruments that were used on tech demos that were then provided to enable the NASA Cygnus mission, hurricane sensing, which comprises of 8 satellites. And TDS-1 and Cygnus were really intended for ocean scatterometry, wind sensing, but they did show, the collections showed that there was great potential for ice, snow, land sensing. And that you can see the progression of the satellites from early days all the way up to Hydro-GNSS. So Hydro-GNSS is targeting land, and it's exploiting more GNSS signal characteristics than previous satellites. So previously, we just used single frequency GPS signals, and we use the left-hand circular polarized reflections. Now for Hydro-GNSS, we're exploring Galileo signals as well as GPS. We have special channels for coherent signals, coherent reflection signals at a higher rate. And we have dual frequency and we have dual polarization. So we're adding on layers of measurements on top of what we had before. So the mission case, the case for Hydro-GNSS is that I probably don't need to tell people here that how important that water-related issues are. They're amongst the greatest challenges facing the population for the future in terms of drought, flooding, biosphere, and climate. And Hydro-GNSS is targeting parameters which have been derived from the essential climate variables. So they're closely related. And so the soil moisture, the freeze-thaw flag, which is classification flag, inundation classification flag, the biomass. So this is above ground biomass, forest biomass. And we also have secondary products, which is ocean wind speeds, and ice extent. And here's an animation that gives a good illustration of what the mission is trying to do. So you can see the targets. The freeze-thaw is a tracer for permafrost. We're aiming to measure biomass from the attenuation, soil moisture, and wetlands or inundation. And the GPS and the Galileo satellites are at a high altitude, 20 to 24,000 kilometers. They're transmitting L-bands continuously down to the Earth. And what we're doing on the low Earth orbit is we are targeting the specular reflections of the four highest gain signals that within our footprint. And we get these things we call delay Doppler maps, which are the source of our measurements. And from them, we apply processes to try and determine and separate out different parameters, the soil moisture, the wetlands, the biomass, and the freeze-thaw, in particular, over permafrost. And the secondary products is measuring ice extent and wind speed over the oceans. A great thing about L-band is not interfered by clouds. And you can see how the signals build up over time. It's quasi-random. It's the reflections between 2 sets of satellites. So we don't have a repeat ground track as such. It builds up statistically so that we get 80% coverage over every 15 days. This sets out the mission and science objectives. The aim is to exploit L-band signals to monitor the Earth's water systems to a finer resolution and derive measurements linked to ECVs defined by the Global Climate Observing System. And so we have the requirements there, which are derived from the ECV requirements. And we're trying to, in terms of resolution, it's a difficult one to answer. Over the ocean, where you have diffuse reflections, we get about 25 kilometers. But the other extreme is where you have a flat river or lake, where it's very, the signals are very coherent. We get down to the Fresnel zone, which is better than 1 kilometer resolution. So we have a wide range of resolutions. We think we work on the basis that over the land, the resolution is around 5 kilometers, but it will vary depending on the surface. And we will be making the delay Doppler maps available and the level 2 products, level 2 and level 3. Timeliness is going to be 31 days, and we're aiming for a faster product that's better than 7 days, with a view towards a future implementation of 24 hours. And yes, coverage of more than 80% in 15 days with 2 satellites. We've had a big advantage in terms of making the case because of the work that was done by TDS and Cygnus beforehand. So there's a lot of evidence already that we can meet these objectives. And I won't go into all the details, but you can see some of the example plots here. We have soil moisture from Cygnus and soil moisture from SMAP, and you can see that they're easy to compare. And this one is very compelling. This is the inundation or water. You can see the SMAP passive is a bit of a benchmark when it comes to soil moisture, but you can see it's quite low resolution. The SMAP active, while it was operational, it got very impressive, very high resolution results. You can see, though, that GNSSR is very special because maybe not quite as high resolution as radar, but it's picking out all the watercourses underneath the forest canopies. Because to SWAT is called dark water, to us is our friend. We like the flat surfaces because we get the strongest reflections off the flat surfaces because it's forward scatter, not back scatter. So it's a very good complement to some of these other radar missions. The freeze thaw, you can see that there's a good relationship between the temperature and the measurements. And when the damp soil freezes, you get a very big change in the permittivity, and that's what we're seeing here. And then the biomass is one that where we have colleagues who are recovering the biomass. The mechanism is that you're measuring the attenuation after reflection. And so there's quite a job in separating these things out, but we have evidence that it can be done. So the science partners have worked together to raise the science readiness level to SRL5 using a simulator that was developed by Sapienza and Tor Vergata, and it generates the observations of it as if in orbit, and we're able to then test out our level 2 processes as well. So we're using it not only to prove the science, but also to prepare our level 2 processes for the active mission. And we've used it first on the well-known measurements, which are validated, but also on the new measurements, which we're a bit less sure about, and to try and get an idea about how this is going to work and what the error terms are. In terms of error terms, then this is a little schematic showing some of the processes. So we're actually measuring the power that's reflected off. We're trying to measure the reflectivity at specular points, so we need to measure a reflected signal accurately. We need to know the incident signal as well. So part of our process is mapping out, modeling what the GNSS satellites are transmitting. So we've been mapping out the patterns of GNSS satellites so we know what their transmit powers are and their antenna patterns. And on board, we have blackbody loads to calibrate the radiometric because we have to separate out the signal from the antenna noise. And we're also applying an onboard digital elevation map that allows us to geolocate the position. I'll probably skim over this, but this is just to give you an idea of what the antenna noise looks like. It's not constant. The antenna noise varies a great deal. We see a lot of signals over the oceans, and this was a big surprise to us when we first discovered this. We think it's the L-band satellites that are transmitting signals all the time. Other GNSS satellites and other satellites that are producing L-band produce these hotspots, which means that we have to take into account this. We can't just do signal to noise. We have to measure absolute signal. And you can see sometimes there's interfering points. I think this is some kind of exercise going on over the Pacific. And we sometimes see strong signals in geopolitical hotspots as well. So we have to take that into account in our calibration. So the progress with the mission, we can see the satellite is coming together now. We have the low noise amplifiers, the antennas here with the dual polarization, dual frequency, the instrument itself, This is the satellite, just taken a few days ago, actually. We've been fitting it together for the first time. This was last year when we were getting the structural qualification model sorted out. So you can see it's about 65 kilograms, and it has high rate data. It expands. It's got accurate attitude determination, propulsion, and it's designed for a 5-year life. And the second satellite is following closely behind. We're expecting to get going in earnest with the environmental testing next year. The launch is baseline for Vega C about this time next year, but we are looking at other micro launches opportunities as well. So in terms of the ground segment, then we have the Mission Operations Center and the PDGS located at Guildford, but we're using comms via Svalbard. So that does give us the opportunity for faster, lower latency processing if we need to. So the PDGS takes it from level 0 to level 2 to level 3. Processors are provided by the science team. We're expecting 6 months for the commissioning, and then after that, we will be releasing the data. It's data that's owned by ESA. Level 1 to 3 will be free and open basis for registrants, and there will be documents and sample scripts available. And we'll have a website as a point of contact. It's actually live as a placeholder website now. If you look up hydrognss.org, but it'll just say watch this space. So nearer the time, we will get this up with all the information that's needed. So I'm coming to the end of my talk, and I think in terms of outlook and recommendations, well, to summarize what I've said is that the ESA Hydro-GNSS Scout, there will be 2 small satellites that will be launched together, nominally the end of next year. It will provide a service of soil moisture, freeze thaw, inundation, and above ground biomass. It has secondary products of ocean wind speed and ice extent, and we're trying to link these products closely to essential climate variables. It's complementary to SMOS and SMAP. These are, I'm sure many people here know and value those missions, but they are both long past their design lifetime. So this provides some kind of continuity, although it's complementary. It's different to the measurements that SMOS and SMAP take. The spatial resolution is looking good. We have the potential of getting, in some cases, down to better than 5 kilometers with a high resolution coherent channel. There's a lot of opportunity there. I think in terms of temporal improvement, really, there's a need for more satellites. 2 is good, but Cygnus had 8. Really, that's the way it should be going in the future, is more satellites. It is low cost to augment. Once the payload has been developed, it's not that expensive. These are small satellites. They could be flown as secondary payloads on other satellites. With the very new measurements, as well as the ones that we know, we are expecting the unexpected. So the dual frequency, coherent, dual polarized data will find new applications. We saw that with TDS and Cygnus. They found all kinds of applications. So we're welcoming people to have a go with the data when it comes down. And working on new processing and calibration techniques may be enabling factors that enable newer products. And then to finish off, a few more in the way of outlook and recommendations. We think we think there's going to be a lot of benefit in extended calibration validation activities. I think there's a lot that can be done. This is a small satellite with a low budget, but there's a lot of potential there. There's reflectivity will behave differently over diverse landscapes. There's all kinds of investigations, the amplitude, noise, geolocation, EIRP. We're looking at using homogeneous ground reference sites for calibrating the level 1 and trying to look at consistency between our satellites and other GNSS reflectometry missions. And trying to extract extra information from the delay Doppler maps, which could be assimilated with models. And at the level 2, again, extended calibration validation activities We're looking to explore collaboration with other missions such as biomass, NISAT, SWAT, RONGO-Y. We could compare products, matching footprints, and there may be ways of applying observing systems, experiments, and simulations to understand the impact of GNSSR measurements. There's many novel applications that we could look at. So in terms of biomass, because we're measuring with quite fast measurements, we may be able to see some of the more dynamic processes, things like forest disturbances from fire or felling. There's ways we might be able to increase the swath. There's assimilation into NWP and land water models, input to permafrost modeling, inland waters, river height. Secondary products, there's a long list of secondary products as well relating to ice and ocean, glaciers, pollutions, plastics, oil spills, and there's more advances that we can make on board because it's largely programmable. There may be possible to apply upgrades to improve the signal processing. We can target new signals, we can change to new settings, and onboard handling of coherent signals. So those things are possible, but we are also conscious we need to provide a stable service. And that's the end of my presentation.
Thank you very much. We'll hold on the questions. We'll keep it for discussion. So we have to move to the next speaker. Thank you, Martin. Very interesting. So our next speaker is Fabian von Trentini. Oh, so actually, he's replaced by another speaker. He will introduce himself. And the title of the talk is Digital Catchment Twins, How Holistic Approaches Improve Decision Making.
Yeah, thank you for the introduction and hello everyone. Well, I'm Florian Wilkofer and I'm from EOMAP, which is a company in Bavaria in Germany. And yeah, EOMAP usually focuses on satellite-derived bathymetry and water quality issues, but we are now also digging deeper into digital twins, and in this case, more like digital catchment twins. And so I have the honor to present you how those digital twins can be a holistic approach to improve decision making. So in general, why would we need digital twins or digital catchment twins? Well, decision makers usually rely on complete information. So what I do mean by complete information? Well, complete means information in time and space, and also lots of information about many different parameters, but also this should be tailored to the user's requirements. And in general, classically OData portals, but also other data portals in general only provide the data. They do not provide any further process information about them. And so their digital twins, of course, come into play, providing a more holistic view, putting all different data information together from in situ data, from data derived from Earth observation data and model data. And especially OData are very valuable in this context because they are valuable over data scarce regions because, well, with remote sensing data, we can go back in time over decades to create some kind of baseline information. We have this information everywhere, basically, even for small water bodies, and those information are timely and affordable. So at EOMAP, our key areas for digital twin solutions are freshwater monitoring, which is the basic water quality and also discharge and data, blue energy applications, which focus on applications for hydropower providers and, for example, offshore wind parks, but also land monitoring then, hydrography and coastal zone management. And for this talk, I will focus on freshwater monitoring and blue energy applications. So at EOMAP, we have currently 2 digital twin projects running. One of them is the HYPOS project, and in the HYPOS project, our portfolio consists of operational monitoring of reservoirs and river systems, near real-time hydrological and sediment states, near real-time monitoring of sediment management activities, and also creating a baseline for environmental information based on historical data. In HYPOS, for this, we use satellite data, of course, which is data from Landsat 8 and 9, but also from Sentinel-2 and Planet data. But of course, we use also model data. In this case, we use the model by the SMHI, the HYPE model, and we also use in situ data, of course. And for the ditch model, we plan to create our portfolio, which consists of water storage monitoring to identify pressure due to different stresses, water quality monitoring using satellite data, and potential forecasting using modeling, but also AI. And of course, we want to have an impact assessment of extreme events, which includes floods, droughts, and algal blooms. Now I want to dig a little bit deeper in our projects. So in HYPOS, the applications focus on how we can support decision makers in the choice of design of the hydropower plants. We can provide near real-time monitoring for management activities, but also for ecological impact assessment. And what you can see here is our online platform of the HYPOS portal that we have. And on the left side, you can see you can choose between several spatial layers. And here you can see turbidity, but you can also select point layers in situ or model data, which you can see here at the various stations, which in this case is this charge. And the user of this portal can upload their in situ measurements or the model data by themselves to display then here. And so you can get a complete overview of the spatial distribution of a certain time step, but also you can get time series, and you can display them all together. So to say, in this case, you can see here we can display the water quality parameters, which consist of turbidity, chlorophyll A, and so on. But also you can, of course, upload your model data or in situ data, and you can display them along with your water quality data. And on this platform, what's also possible is that you calculate different parameters on the fly. In this case, it's a sediment flow, which is a combination of the model or in situ data for discharge and the EU-derived turbidity data. Furthermore, we can also use the portal to support routine monitoring, in this case for environmental impact assessment. What you can see here is the Caurabassa reservoir in Mozambique, which is one of the largest reservoirs in Mozambique, which spans from west to east, more like over 100 kilometers. And what we wanted to show here is that, well, the water quality or ecological assessment here is very difficult if you would use in situ data or point measurements, so you wouldn't get the entire picture. So that's why we step in and provide satellite-based data. In this case, you can see again turbidity. And also what you can do is you can define your own virtual stations, as you can see here, and then plot time series of the content of these stations here. In this case, it's also turbidity, and then you get a full picture of the temporal dynamics of the turbidity, but also the spatial dynamics in this reservoir. And what you can see here is that, for example, at the inlet of the reservoir, you have very high peaks in turbidity, but a quick decline in turbidity. But at the outlet, for example, in the middle of the reservoir, you have less turbidity, but it declines slowly. And now I want to show what we plan to do in Ditch. So in Ditch, we want to create a concise online portal for which comprises then EO data, which themselves comprise water quality, water level, land use, and so on, but also measurements, in this case discharge, but also meteorological in situ data. And what also comes in place are climate model data, which are available. And we want to use them for short-term predictions or long-term projections, depending on the topic. If we want to have predictions, we use forecasting data. If we want to have long-term projections for climate change, we can use actual climate model data. And then we feed the hydrological model with the data based on EO and the measurements, but also we use the data themselves to validate the hydrological model. And then we want to combine all this in this concise portal. And well, we want to do then bring all the data together and let the user decide what he wants to use, so it doesn't get overflown with information, so that he can get a better decision support tool for their decisions and tailored to what he wants to use. And yeah, just give you a short example of how we plan to implement this. For example, here we have a warning portal in plan, in this example for sustainable river ecology. And well, we created this based on a event where we get some data. And in this case, it was the river fish kill event along the Odra in 2022. And what you can see here, this fish kill event was caused by large algae blooms along the Odra. You can see here the river course from the spring to the coast. And you can see here the times. And yeah, what you can see here, we have a large algae bloom in July, but also kind of at the same time, 3 algae blooms at the lower part of the Odra in August. And well, this event was caused by many factors, which by themselves, none of them would have caused such an intense algae bloom. And yeah, with our early warning portal, we put all the data together that we could get, like satellite data, water quality, water level, and so on, but also hydrometeorological data, in situ data, and modeling to create a base for a monitoring system so that we can recreate the data or the event for further monitoring, for future monitoring. And how did we do this? Well, we derived hydrological data from Earth observation data, in this case, Sentinel-3, as you can see here, the discharge time series from Sentinel-3, but we also derived water level and river width, depth, and flow velocity. And then we combined this with meteorological observations to establish some kind of empirical relationships between the data, the observations, and the EO-derived data, to which then in turn serve as indicators to detect critical environmental conditions. So what you can see here is then this monitoring on early warning system. And I will go into detail further, but in this case, you can see here as an example, a water level sunshine duration indicator, which is a very empirical indicator, but it implies a beneficial condition for algae bloom. So now let's go into more detail about this warning portal. On the left side, you can see several virtual stations, which are used, which can be defined by the user himself. And on the right side, you can see the spatial distribution along the Odra. And yeah, what you can see here now is you can select a date and a time frame where you want to go back in time. And you can see here then in the display the current state. So whether there's a threshold exceeded where it's an alert, or whether the threshold is exceeded where it's only a warning. So you can see it for the different stations, but you can also see it like in the spatial distribution. And for example, here we have accumulated 7 stations because the virtual stations were so close together, it's not possible to display them here any better. What you can see here that out of 7 stations, almost 2/3 show a critical state. And here, further upwards on the river, only 1 station showed a warning state. Yeah. And then I already come to the conclusions. What are the key benefits of digital twins? Well, for once, you can get a holistic view. You get sound information on the entire catchment. You have more accurate data, so you have historical information. You have data to use for validating existing data or even to fill data gaps. You can create an early warning system by monitoring and or forecasting of key variables to detect critical states. And of course, you have a kind of flexible workflow through the integration of multiple sources of data, and also you can create a customized reporting. And all this leads then to better data to improve economic and environmental evaluations and summarize them for decision making. And also you can have better data then to evaluate faster and at lower cost with less risk than before. Thank you.
Okay, so we do have some time for questions. Yes, we have someone in the back.
Thank you very much for the interesting presentation. I'm really happy to see a lot of the buzz around digital twins, a lot of efforts, but at the same time, I'm a little worried with all those different efforts going on. How are the users, whomever they are, going to pick which one they have to use? And I'll leave it at that.
Yeah, that's. I mean, it's always. We have more or less like authorities or other companies that have specific topic in mind and specific variables or parameters they think would describe the best of how it would benefit them for their decision making, right? So let's say a common user, it might be impossible for him to figure out what he wants to know, right? So you have to have a kind of a background, what you want to know. And I guess because a digital twin could offer lots of things, right? But the purpose here for us is that we focus or display only what the user really needs for what he wants to assess, right?
You have other questions? Is that one coming? Yeah.
Thanks for the presentation. So what I would say is one of the things that we want to emphasize as part of the digital twin is we want to develop a process-based architecture that captures earth science processes, not just try to focus on cheaper, faster, and in-time decision-making things. Those can be two separate things for decision makers, but digital twin needs to capture all the relevant processes.
Yeah, that's true. But on the other hand, then not each and every, I mean, in the background, you can gather all the information that you have, right? But what you display then to the, let's say, a customer, right, is a totally different thing, right? The customer can then select what he wants to have out of this digital twin, which contains all the information there is, basically, for catchment, right? But you might not need each and everything of that data that you have at hand.
Yes, we have a question here.
Thank you very much, Florian, for this lovely presentation. On one of your slides, you said that you derive flow velocities from EO data. Could you tell me a bit about how you did that?
Unfortunately, I cannot because I was not involved in the derivation of how we do this.
Do you at least know which data goes into that?
I guess it's a derivative of the Manning equation, I guess, with all the with the
Right, so it's not a direct
profile and
retrieval.
the profile and so on.
All right.
So I guess it's just a derivative. It's
And since we have 1 more minute, maybe what do the risk numbers mean? I didn't understand. There were some numbers on your risk slide.
yeah.
What does it mean,
This one?
214?
Well, it's just this one, you mean?
Yeah, the
It's
numbers.
basically just the value of the risk factor. So we calculate, it's a very simple risk factor in this case. So we have the water level divided by the sunshine duration, so to say. And so it's very empirical. It has very little physical background, right? But it's only to illustrate, well, we have low water level, we have high sunshine duration. And if that's the case, it's very beneficial for algae bloom across the river to occur, because when we have lower river levels, the possibility for a low discharge is given. So it's a very high risk that the algae bloom will just stay at point. So
Thank you.
yeah.
Thanks a lot.
Thank you very much. And so our next speaker is Yusuf Jessi, and title of his talk is Opportunities for Lake Ice, Remote Sensing from Current and Future Global Navigation System, Reflectometry, GNSS-R missions.
This one, right? Okay, you can use it.
Okay. Hello, everyone. My name is Yusuf. I'm doing my PhD. I'm a fourth-year PhD student working with Claude at the University of Waterloo, Canada. And as he mentioned, yeah, my topic is on the application of GNSS reflectometry for lake ice monitoring, different aspects of lake ice, physical properties. The presentation would start with an introduction to GNSS reflectometry and lake ice remote sensing. And then we move towards some results that we have already achieved. And we'll talk about some challenges and opportunities that we have in GNSS-R missions for lake ice remote sensing. And then I finish with conclusion and outlook for future works. A range of importance has already been listed for lake ice, including climate modeling and weather prediction. Also, economic aspects, including ice fishing and tourism, and also northern transportation, which is totally dependent on the ice cover duration and also lake ice thickness. And lake ice remote sensing is being done by optical and also microwave sensors. And GNSS-R, GNSS reflectometry, as Martin mentioned, is one of the newest ones and the most recent techniques for lake ice remote sensing, or lake ice monitoring. And as you can see in this picture, you don't need the transmitter, as Martin said. There are some signals in space, not initially designed for remote sensing applications, but yeah, there are already in the space, and we just need to collect them. That's why it's called signal of opportunities, or SOOP. Depends on the literature that you use. Yeah, thank you, Martin, for providing good introduction, so I don't have to go through that anymore. And here is a list of GNSS-R missions. Well, except for TDS-1, other missions, yeah, actually there are a few examples. Other missions are operational, currently operational, and all of them, yeah, are working at the low elevation orbit. They are small, and they can be working either as a single satellite or as a constellation of satellites. Like HydroGNSS that Martin mentioned, it consists of 2 satellites, and Cygnus contains of 8 microsatellites. And the main observable of GNSS reflectometry is delayed Doppler maps, or DDMs. Well, the GNSS reflectometry receiver may receive direct and reflected signals, and this is a graph for the autocorrelation function. The first one is this one. There's autocorrelation between the direct signal, this one, and a replica of the GNSS code. And the second one is the same, but with the reflected signal. So the autocorrelation between reflected signal and a replica of GNSS code. And since we have roughness on the reflective surface, we have reflection contribution from several sectors or several positions, and all of them together gave us DDM, delayed Doppler maps. And here are two examples of DDMs, which can be used to interpret the type of reflective surface. And as you can see here, sea ice has, new sea ice, New Year sea ice, has a very low roughness. It's smooth. So we have a dot-shaped DDM. And for open ocean, we have a horseshoe shape. It's just a very simple example to show how DDM can be used to discuss the reflective surface. And also, rather than the DDM shape, we may derive some parameters from DDMs related to the power of the reflected signal, like SNR. And all of them together can be used to monitor lake condition. Lake, if it's lake ice or if it's open water. And based on this introduction that I provided, we have already conducted 3 measurements over lake ice. The first one, we used Cygnus data over Qinghai Lake and Tibet Plateau in China. This is the largest lake in Tibet Plateau experiencing freezing cycle. We have no access to northern lakes because Cygnus only covers up to 38 degrees in latitude. So that was the best candidate to work on. And we analyzed DDM SNRs over a 4-year of observation, 2018 to 2022. And a pattern could be seen for the specular tracks. Yeah, I don't know what happened to you. Oh yeah, it's here. And we can see that as the lake transitions from open water to lake ice, we have a change in SNR values. Also, a comparable pattern can be seen in breakup period as the lake transitions from lake ice, fully frozen, to open water. So we analyzed the 4-year time series, and we see this up and downs, which is in harmony with temperature. And then we compared them against freeze up and breakup dates obtained from MODIS images. And we reached these uncertainties. For example, 6 days for freeze up start. This is the uncertainty that we have. And also for ice covered duration, we have 0 day or 5 days. Well, in terms of the statistics that you're using. So we reached acceptable uncertainty for lake ice cover or lake ice phenology analysis. Full details can be seen in this paper, which was published 4 weeks ago, including the sensitivity of Cygnus and GNSS reflectometry to melt onset before the actual breakup. The second study that we had was using Spire grazing angle data for Great Bear Lake during summer 2021 to see if it's sensitive to breakup period and fractions in lake ice before breakup, during breakup. And we analyzed around 70 or 80 tracks, specular tracks over Great Bear Lake. This is an example of the fully frozen lake. And this is an example of the lake during breakup period. And as you can see here, there's a drop in SNR here. So Spire is sensitive to, to lake surface condition. Also for Great Slave Lake, another Canadian lake. This is an example over fully frozen lake. And this is a track over the lake during breakup period. And these changes can be seen, which confirms the sensitivity of Spire to lake surface condition. And the third one, which is currently being done, is a collaboration that we have with SMAP-R, another GNSS-R mission, for analyzing lake ice and also open water. And we chose 4 Canadian lakes: Great Bear Lake, Great Slave Lake, Lake Athabasca, and Lake Winnipeg. And we have access to 7-year time series, actually 8-year time series. And we have a variety of SMAP-R observables. It's not like Cygnus that we only had SNR. We have Stokes parameter and child Stokes parameter as well. And we start working on assessing the sensitivity of a SMAP-R to lake surface condition, lake ice phenology, and lake ice thickness. These are some examples of the results that we are currently working on. This is the sensitivity of all SMAP-R parameters to the lake surface condition. And as you can see, as it moves towards the breakup, we can see some changes in some parameters, not all of them, for example, not this one, but most of them have sensitivities to lake surface condition. And this is all data together, all 7 years together, against the average breakup and freeze up timing, along with an MTT analysis, which is a statistical test, a moving t-test, which is used for lake ice phenology timing. We have already used that in a paper, in Cygnus paper, I talked about 2 minutes ago. And also, this is the sensitivity of all SMAP-R observables to lake ice fraction obtained from CIS. For those of you who do not know, CIS is a data set for more than 100 lakes, northern lakes. It's a weekly report containing the fraction of each lake. For example, if 10% of lake is frozen, it says it returns 10% for this lake, but actually 1 out of 10. So we use that to see the sensitivity of SMAP-R observables to lake ice fractions. So we do have some challenges in reflectometry applications for lake ice remote sensing. The first one that I just mentioned in Cygnus study, northern coverage is a challenge in Cygnus. However, in recent missions, we no longer have this issue. Also, we have an increased number and also types of observations. As I mentioned, in Spire, we have grazing angle observations, which can be used for GNSS reflectometry and also GNSS radio occultation at the same time. This is an example of Spire tracks over Great Bear Lake only in summer 2021. A high number of tracks give us a very good temporal resolution. Also, some new missions has introduced digital elevation models to their missions, which helps to have a better performance for DDM shapes. It's no longer going to move towards negative delays like the one that I have from Cygnus. This is an example from Cygnus without DEMs, digital elevation models. And also, it helps to have a better point positioning for specular points, since we're going to aggregate our data with some other auxiliary data and we need to know the exact position of a specular point to have a better aggregation and also avoid land contamination. So we can make sure that the specular point that we are working with is exactly from the lake. And some coherence detection methods have already been applied to some missions like HydroGNSS, which overcome the issue that we have with SNR unreliability and errors that again Martin just mentioned. Yeah, as you can see here, if we do DDM coherence detection on board, we probably have this opportunity to detect lake ice from open water, and we may also use some other measures like coherent power ratio or some SNR values without those errors, calibrated SNRs. So as a conclusion, we worked with three types of GNSSR missions for lake ice monitoring with a variety of results. And also, we know that what we are coming based on the current and upcoming missions, GNSSR missions. So based on this conclusion, we have three recommendations. The first one is starting collaboration with upcoming or actually recent missions like HydroGNSS and Aspire to have access to lake data, and we may ask them to include lake ice to one of their targets for their upcoming projects. Also, we may use GNSS reflectometry to upgrade some models, some lake ice models, modeling how lake ice interacts with signals. So they can be upgraded by adding bistatic radar configuration. And we may apply machine learning algorithms for lake ice detection by using either the DDM shape, analyzing the DDM, or analyzing the parameters that we can get from DDMs. Yeah, thank you very much.
Okay, so we do have time for questions. Yeah, maybe I'll have one. I'm being the supervisor. Could you explain to the audience a bit more about the parameters that are derived, since we have time, derived for the SMAP R?
Oh yeah.
Go back to one of the slides just to.
Oh yeah, sure. Well, SMAP R, well, it used to be SMAP, just SMAP, and they had an antenna for soil moisture detection, and it was passive, and the antenna was L-band, and then it turned to be a reflectometry mission after it failed to do its initial project. So it's not like a GNSSR antenna to receive left-handed circular or right-handed circular signals. It's linear. And then the analyzed outputs that we have out of SMAP are, as he mentioned, are Stokes parameter and child Stokes parameter. S1 to S3 is a Stokes parameter and some child Stokes parameter. And they may have different patterns and different behaviors over lake ice. And some of them have similarities to each other because they are derived from each other, some of them. So as you can see here, for example, S1, that one, S1 is very similar to Chi here, this one. And based on this sensitivity, we may have different interpretation from lake surface condition. For example, as I said, S1 and Chi, their pattern can be used to detect the breakup period. Here we have a big jump during breakup period. And normalized by static radar cross-section, NBRCS, can be used for both periods. As you can see, we have 2 jumps during freeze-up and breakup periods. Yeah, we have more observables than what we had in Cygnus and Spirens. Just we had SNR or some related parameters to SNR.
Have other questions? If we have 1 minute, actually, I will ask you to show the correlation maps. So you produce some correlations between.
Oh yeah, of course. Yeah.
So CIS is the Canadian Ice Service in Canada. So it's they produce these products. So what can you draw as the main point from the correlations you looked at between the different parameters and the ice fraction from?
Yeah, of course, it talks about the fraction of ice as, for example, during freeze-up periods. This is for freeze-up. As the lake transitions from open water to fully frozen, every week we have a fraction of lake which is frozen, and the correlation between each parameter to that fraction is presented here. So it can be used to detect the sensitivity of each of these SMAP-R parameters to the ice fraction before the ice gets fully frozen, the lake gets fully frozen, or before the lake gets, transitions to the open water. Yep.
Okay, thank you very much. So we have the next speaker. We have Valentin Foucault, and the title of his talk is Innovative Autonomous UAV Solution for In Situ Cal-Val of Satellite Altimetry over Inland Waters and Other Surfaces.
So good afternoon, everyone. First, I want to thank you for giving us the opportunity to present this R&D project. So I want to thank all the co-authors and all the people that work on this project. So Jean-Christophe and Yannick from Vortex, but also all the people and all our partners from ETEC Group, Loïc and Laurent and Pierre-Louis that is here today, and that's went here to show the drone all the week. And I want to say a big thanks to Nicolas and Cedric from CNES to make this project possible. So I'm going to present you this project to develop an autonomous solution UAV based for in situ Cal-Val altimetry. So it's an enhancement of our actual solution that is on the room just next door. So, as I said, it's a project led by CNES. It's a cooperation between Vortex and ETEC Group. We want to develop a new solution. So the solution is a combination with a sensor that is developed by Vortex and a drone solution that is developed by ETEC Group. So why we use a drone for altimetry activities? So moving sensors are very useful and required for Cal-Val activities for many reasons. The first one is that in situ sensors are not always located exactly under the ground track, and on strong topography rivers, the slope correction must be accounted to make the data comparable, the measurements comparable between the in situ sensor and the altimetry measurements. Also, there is the satellite drift, and the satellite not always perform its measurements exactly at the same location. So even if the in situ sensor is located just under the ground track, The actual position of the satellite measurements will be around like 200 or 500 meters away, and the slope must be accounted to correct it. And we have seen in the framework of the street art project that topography of the river evolve during an hydro cycle. So we need multiple topography measurements in order to account of this evolution during the hydro cycle. And to do all of these activities, drone is a flexible solution with a low cost and easy to deploy to perform all these measurements. So we have an actual solution that is working on the field. So it's, as I said, a combination between a sensor and a drone. So the drone has 30 minutes autonomy and can fly with a wind up to 50 kilometers per hour. And today, the altimeter has two sensors, so LiDAR to perform centimeter level height measurements, and the altitude is retrieved by GNSS positioning. And we also have a camera to perform water masks, water photos, but also water surface velocity measurements. In Vortex, we want to develop this altimeter. So we have a lot of R&D activities ongoing. The first one, and it's going to be done in a few months, is developing a new generation of this altimeter with these two sensors to make the deployments easier. Then we want to adapt this sensor to measure water quality with moving sensor. And the end goal of this moving sensor is to develop a bathymetric LiDAR to measure discharge with the combination of height, flow, and bathymetry. This solution is deployed on the field for 3 years, and we perform various deployments on different locations, on lakes, on estuaries, on a lot of different rivers. We perform 24 campaigns in Europe, in the US, and also in Greenland, and for a total of 550 kilometers of river profile. So we acquired, together with ETEC Group, a strong experience for the organization and the processing of all this amount of data. In these 24 deployments, we have performed two very big deployments. The first one is on the Willamette River in the framework of the Swartz-Calval activities. So we performed 35 long river profile during 3 days. So it was a big deployment in a short time range. It was quite a challenge, but the data we acquired were really useful. And then you probably heard a lot of this super slide presented by François, and also during the SWOT session. We perform in the framework of the street art project and also for Swartz-Calval activities, multiple river topography measurements on the Marman super sites in order to measure the evolution of the water topography during the year. This solution is also used on other surfaces. So we performed a deployment in Greenland, as I mentioned, to measure freeboards and sea ice roughness. So this deployment was a big challenge for both Vortex and ETEC. Because it was the first deployment on Arctic conditions for both drones and altimeter. But everything went really well, and we had like very good results on this deployment. So our solution can be deployed on Arctic conditions. The other surface is ocean, and to be more specific, coastal zone. So we can measure sea surface height and retrieve directional wave spectrum from these measurements. So to do so, we use two drones with a vortex altimeter, not only one. And we can deploy very easily from a boat, but also from the coast, because we can deploy up to 5 kilometers from the coast. And this solution on ocean works really well. We performed our last campaign on ocean this month in Saint-Jean-de-Luz in south of France. With a good drone solution, why do we need to go further? Why do we need autonomous drone? The first reason is that we want to perform measurements collocated in time and in space with altimetric satellites. So to do so, we have to deploy at a specific time, and only an autonomous solution can do so. If we want to use the actual solution, we have to deploy on the field a team of drone pilots at a very specific time. Then, as we have shown in the street art project, we need a lot of different river topography measurements at different water level. And to do so, we have to go very often on the field to measure the exact same river profile. And autonomous drones are really helpful for this. And to deploy at very large scale, because we need a lot of in situ data in altimetry, autonomous drones are less expensive than drone pilot teams on the field. If you want to have several river profile measurements at the same time everywhere in Europe, we will need to have many drone pilot teams, and autonomous drone can decrease the cost of such deployments. So, as I mentioned, this solution is fully programmable. We can have different flight plans, and we can make the drone perform measurements at the exact same time and location as the satellites. The autonomous drone can also be used as a fixed in situ sensor, where it's impossible to deploy for many reasons. It's impossible to deploy pressure transducer or vortex microstation. This solution can perform measurements where in situ sensor can't go. So to be a bit more specific, the drone part of the solution is the combination between a drone, a DJI M30 that is smaller than the one you can see at the entrance of the room, and a dock, a box that protects the drone, that also perform weather measurements to ensure that the drone can fly, that the conditions are not too heavy for the drone. So the autonomy of the M30 is around 40 minutes, and it can perform deployments every 2 hours. Now I'm going to do a little status of the ongoing development of the solution. So on the vortex side, so on the altimeter side, we have to miniaturize the actual altimeter because the drone is smaller, and we have to make it fit in 8 by 5 centimeter rectangle. So it's a big challenge, and we are going to develop a custom PCB to increase the robustness of the altimeter. But autonomous drone means a lot of data arrive automatically. So we are going to develop connected full ground segments to process all this amount of data and to perform all the processing at each deployment. Also, we are going to develop a dashboard to follow the health of both altimeter and drones. So we're going to add features on existing dashboards to monitor the solution. On eTech Group side, this is also a big challenge because it's the first use of a DJI dock in France. So they are actually performing a lot of tests to verify the technical specification of the DJI dock about the autonomy, about the weather condition, about everything. They are going to try to test everything. They also have to remove the actual payloads of the GI-M30 and develop a custom gimbal to ensure the stability of the altimeter. And they finally, they're gonna integrate the sensor and the gimbal under the drone. And together, we are going to perform a big campaign, a test campaign, to ensure the good behavior of all the system, the dock, the drone, the gimbal, and the altimeter. So, sorry. Oh. There is a problem. Oh, sorry. So this is a view of the dashboard to follow the autonomous solution. So the green dots are the flight plan of the drone. It is following exactly the river. On the top right, you can see the FPV view of the FPV camera of the drone that is exactly overflying the river. And on the bottom left, you can see a view of what is the LiDAR measurements at the exact same time. So this is first example of what the solution is going to be. We will perform measurements at a very strong rate, and we'll perform it everywhere it is possible. So to conclude, we are developing a flexible solution for hydrology that can be deployed at a very large scale for hydrology, but also this solution can be used on other surfaces as sea ice or in coastal zone. There are many use cases for this solution, for Calval activities, for SWOT, for Sentinel-3, but also for Sentinel-6. And this solution can be really useful for the development of new mission as Sentinel-9 Crystal, or the next generation of the Sentinel-3 mission. But this amount of data can also be used for science activities as the calibration of hydrological models. So to finish, I just want to tell you a little bit about the timeline of the project. We aim to finish the prototype in the mid-2024. There are a lot of activities that are ongoing now, and we aim to develop, to deploy the operational solution at the end of 2024. But thank you very much for your attention, and if you have any question, please ask, and I ask Pierre-Louis to come with me to answer all the questions about the drone and the dock. Thank you very much.
Okay, thank you. Okay, so we'll start yes, we have 2 ands, 3, 4. Okay, so we'll start with first. There's the first one here. And then...
Thanks for the very nice presentation and very inspiring solution. We have a similar task in Poland. We fly also LiDAR drones over the other river as Sentinel-3 passes. So it would be nice to look at them jointly at some time. But my question was, on one of the first slides, you showed that you determined the water level from LiDAR data. And my question is how? Because the LiDAR doesn't really reflect from the water. The signal is rather absorbed. And you wrote something about GNSS measurements. So that's the second question. Do you need ground control points on the location, or do you use RTK from the drone only?
To answer first the GNSS question, so we have a GNSS base to perform PPK positioning, to have a very precise positioning of the altimeter. And the LiDAR we use is reflected by water, and it's not a scan LiDAR, it's a LiDAR with beams. We have 8 beams that are reflected by water. So we perform very precise water surface elevation measurements. And we will be pleased to deploy this in Poland and to perform joint campaign.
Thank you very much.
Okay, we have someone else who's walking to the microphone. Please, maybe you want next one to the other microphone.
Very interesting work. I am interested in to know what is the maximum wind velocity that the drone support. For example, I am interested in to have the directional wave spectra during storms. So I would like to know what you can say.
Yes, so with those products that are product on the shelf, I would say that the maximum wind velocity is around 15 meters per second, so more or less between 30 to 40 kilometers per hour. So for the storm application, it would be difficult to deploy those same system. We have some drone suppliers that are working on solution dedicated to windstorm. But in our fleet, those US are not fitting this use case. Sorry.
And the team is prepared for extreme events? Can support this bad weather? I suppose yes. No? Well, also I would like to know what is the spectral resolution of the directional wave spectra? It means how many directions and how many frequencies can you provide?
I don't have the figure in mind, but I will please to discuss this later with you. I have to check this again, but I will find the answer shortly.
Okay, another question, please.
Yeah, part of it was that, the speed, but I was also thinking about intense precipitation like we are having right now would be a problem. This kind of...
For the drone, it's IP55. So I would say normal rain is okay, but the rain of Portugal is quite strong. So I don't really know, but there are other, those drones can fly under the rain, it's sure. We have to make some more tests to qualify what is the quantity of rain it can support.
Yeah. And on the altimeter part, it is designed to match the rain rates that the drone can fly under. So we try to make it as robust as possible about rain.
Okay. Do we have another? Yeah, we had another question. And we're falling into the discussion there, so anyway, go ahead.
Okay, thank you. Really boring. No, really interesting presentation. Yeah, you can try out the heavy rain thing and I'll learn from your experience whether it works. But you said you using the camera for surface velocimetry. I wondered whether you're doing that whilst the drone is in motion or only when it's stationary. And a secondary thought, sort of related, whichever way you're doing it, is have you done any investigations into whether raindrop patterns on the water immediately affect with the flow and therefore could be tracers? But
for the first question, yes, the idea is to measure the flow during when the drone is flying, and we measure also the speed of the drone. So we want to get the speed of the flow by combining both.
We definitely need to talk about that.
Yes, with pleasure. And we have never performed this test with the rain and the impact of the rain on the water, but that's a very, very nice idea. And I think
it makes a good, well-distributed tracer, but I don't know whether it affects with the water immediately.
So it's gonna tell us that we have to definitely deploy under the rain.
All right, thank you.
Thank you.
I'm just gonna complete the answer within the frame of the video. You have directly with a text file associated to the video, the position of the drone, the velocity, the altitude. So it could be very simple to manage the difference of the positioning of the drone.
So before we move to discussion, maybe is anyone had a question for Martin on the HydrogenSS mission? Yes, there's one question in the back.
Yes. Could you tell a little bit more about what kind of rivers and lakes in terms of size you think you can study with this system?
Yeah, the size of rivers, I think we're still kind of exploring that because it was a bit of a surprise when we first discovered that we could. Originally, we thought the resolution was going to be about 25 kilometers, but it was Clara Chu in well, she was in JPL then UCAR, who discovered that it was very high resolution, much higher, and it's down to the Fresnel zone, and the Fresnel zone for L-band is 500 meters, but you do get a kind of ringing effect, so it's not easy to get down to the 500 meters. Conversely, if there is a strong contrast between a strong reflection and very weak returns from, say, forests, then it can have a very sharp contrast, and you can see some quite small distances. I can't tell you offhand, but I know that one of our science team, Estelle Cardelac, was looking at case studies where they were seeing small river features, which was probably less than 500 meters. I can't remember what it was, but it was surprising how small features that could be seen if there's a big contrast.
Yeah, another question?
Thanks, really interesting stuff. You mentioned a delay Doppler map. Anytime I hear the word Doppler, I get excited because I can use it for measuring river flow. But what is a delay Doppler map?
Yeah, I think we and Yusuf also showed some. So it's the kind of measurement that we take at level 1, and what it is it's the mapping of the signal onto the Earth. You have contours of delay as you go further away from the reflection point, and you have contours of Doppler, and so when you plot those out, it makes this over the ocean. You have this kind of parabolic shape, and each of those points corresponds to a point on the surface. Unfortunately, as you go further away from the peak, it becomes ambiguous. You can have 2 points on the surface that have delay and Doppler. So your next question is, does that Doppler contain information about the surface motion?
Doppler, I mean, I'm a bit of an ignoramus about a lot of these things, but Doppler is caused by motion, right? So what's the moving?
It's the motion of the receiving satellite and the transmit satellites.
Okay.
Dominated by the receiving satellite.
Okay.
But there will be a component from the surface as well. But as we discussed before, with forward scatter, unfortunately, it cancels out the dominant term when you're doing forward scatter. Back scatter, I believe it doubles it. So, but forward scatter. So if you go away from the specular point, then probably the information starts appearing in there. But fundamentally, it's a mechanism that sort of cancels out the velocity measurement, which is not what you want to hear.
We'll have it for the Mark III version. That'll work on streams 5 meters.
Okay, thank you. So I'll put up on the screen our seat questions, and then we'll invite the audience to stand up and. Okay, so we had of course 3 big questions, and then we have under that some smaller aspects. So there was regarding the spatial and temporal resolution of products. Which hydro applications are still limited to the spatial and temporal gaps in EO data? Any comment? Yes, please go ahead. I think probably
I just want to stay there.
Yeah, maybe I will.
He's
I'll sit here.
He's had 2 coffee already.
I haven't had any coffee since this morning. No, my question is actually kind of related to my last point there, which is, or rather my point is, small rivers and rapidly responding things. We've got to become more responsive, and I understand why we talk about small rivers being 100 meters wide, but I come from a country where that's the biggest river, and we want to use we want to use these technologies. So I think we've got to be ambitious, and we've got to frame everything we do with a belief that like smartphones. I mean, who would have thought 15 years ago we'd have the capability we have in smartphones? And I would apply the same thinking to everything we're doing. So those are my challenges.
Thank you.
Other thoughts on this?
Okay. So what are the barriers to development of gap filled hydro products? Well, gap fill, was it in time temporal or?
So
it-
spatial and temporal. So I'm coming from the flood mapping community, and I always find it really, we have this problem of like process representation, that we do not represent all the processes that lead to flooding, for example, but observations are process agnostic. And so if we could have more gap-filled observations, that would mean that we have a more complete representation, but somehow we don't have them, despite having a bunch of these access to compute resources, cloud platforms, what have you, so much machine learning. And I wonder why that is. Feel free to.
Maybe we need hundreds of these.
Oh, this one. I think from an optical side of things, when we develop products, either I work on the cryosphere, so if we either develop a snow products or lake ice products, and of course, just cloud cover is an issue. So I mean, there's been some literature, a few papers that do propose methods, but it seemed that we don't, for a few exceptions, we don't see products that are gap filled. So what needs to be done?
A wacky idea, and since I'm sat next to the mic now. How many groups have explored the prospect of mounting useful sensors on commercial airliners? Does anybody know? These things are flying everywhere. I saw just this morning that it was almost triumphant that more flights had flown in California or in the USA in the last week than had ever been recorded for, by like 10%. Right below was one of a glacier that no longer exists. Whether these are related, I don't know. But these planes are flying everywhere. Could we put sensors on them?
I remember having this conversation with someone, but I think there are legal issues in putting. I think we will have a more specific response.
Just give a couple of examples of that. There's a system called AMDAR, which is what you were going to say, was it? And there's probably people here who know more about it than I do, but as far as I know, it is it takes weather measurements, I guess temperature, pressure, and humidity, and it flies on a lot of commercial plane flights, and it's semi-commercial. I think it's something that's coordinated by the World Meteorological Organization, and people noticed it when COVID happened and all the planes stopped, that suddenly there was a lot of measurements missing. And that was the first time that a lot of people heard about it. But this was when some of the measurements from Spire were donated, and it helped fill some of the gap with the radio occultation. So AMDAR is an example that is up in the air, it's working. I think it's primarily the ascent and descent of planes rather than the high level. Yeah. So you get measurements off all the planes that carry it. The other one that I was going to mention is we don't have anyone here from New Zealand or Michigan, because there was a NASA partnership with New Zealand, and they're flying GNSS reflectometry on one plane that's an operational plane in New Zealand, and the project's called Rongo Y, and they're gathering. They've been doing it for a year now, and they've been gathering GNSS reflectometry measurements over the land and taking measurements similar to what I was talking about with hydro-GNSS. So they are interested in expanding the idea further, but at the moment it's just one plane in New Zealand.
Thank you. Right, so perhaps we could move together. Maybe
Yeah,
you want to
Calval.
say something about the cold environment stuff.
Right. Well, definitely that's always an issue. We work on retrieval algorithms, we generate products, but when it comes to calibration, validation in cold environments, that's always missing. So identify that more as a gap. Any solutions proposed? Definitely funding from people who do Arctic fieldwork. But what else? Well, what's in cold regions, one of the challenges, of course, is access and funding to operate some of these the field measurement campaigns. What about the global south? We had the other questions. How can the Calval networks in the global south be improved?
I think there is just one force map in Australia, but otherwise there are very limited ones in the south. Were there ideas from people?
So any people involved in Calval and facing challenges or? No one does field work.
Oh.
But yeah. Okay, so maybe there's less of a discussion point here for this one. If we move into the EO and model integration, we've seen a presentation this week about modeling and how some of the EO data was being used as part of models. So what are the barriers? I think it was one of your questions. What are the barriers to scale relevant model EO integration implementations? When you think about Earth system models or hydrological models, I guess with the scope of this meeting, I think we could focus on hydrological models and what are the some of the barriers.
So I think one of the discussions in the hydrological prediction community is surrounding how we keep building disconnected models and then are very surprised when several processes co-occur, leading to much larger events or cascading events, and then kind of wonder why we are unable to predict them. And so do we really envision a system where it's completely integrated vertically, where we have this kind of Earth system model that's simulating all processes? We have all of these water cycle. So the goal of the session was these novel technologies in water cycle research. Do we envision a future, or do we even need this? In the opinion of the community here, where we have this kind of integrated solution, the digital twin, for instance, that was shown also today, focuses, for instance, on hydrology, but we know that processes such as meteorology, hydrology, hydrogeology, they feed off of one another. And so do we envision a near future where we would have this kind of integrated solution? And if we do, where are we on this pathway, and what are the barriers that are stopping us from getting there? I think we're in the last session.
Right, exactly.
Fatigue and,
or between
yeah.
between us and the
It's you just need to endure for 3 more minutes.
Okay, but I would actually probably ask the question then to the presentation on the digital twin. Add a question which maybe relates to that is, I think it was said that was it HYPE, the Femicement HI that's being used as part, who was presenting?
Florian Wilkoff, I do not see him in. Right.
Oh, he's left. Okay. Because I wasn't sure where the model came in with the data, and so that was going to be a question that kind of fits within that that theme. Okay, so if there are no other questions that or comments, then
we could close the session.
we'll close the session. And thanks very much to all our speakers.